Multithreading is an important concept in computer science. In this course, you'll learn everything you need to know about multithreading in Java. But the concepts apply to other programming languages as well. For each concept, you'll learn the theory and then see some code examples.
Hello and welcome. I hope you are doing super good. My name is Ramendu and I'm working as a senior engineer with Uber. I have been programming for more than a decade now. I believe that multithreading is one such concept which is way too abstract and difficult to understand if it is not taught in a proper manner. However, if the concepts are explained with relatable examples, it becomes a fun and engaging experience. That's what I have done in this course. I have broken down the difficult and abstract concepts in simple English which is really easy to understand. To make the things even more clear, I have presented relatable examples. I strongly believe that multithreading is one such tool which should be in the toolkit of every good programmer. The entire video is split in smaller sections wherein I teach about a particular topic. Each topic is explained with some theoretical concept followed by the examples, and then I implement the topic of discussion in Java to give you a proper working code example. The topics are taught in a bottom-up manner where I start from the very basics and then I build on the concepts layer by layer. By the end of this tutorial, you would become very confident and comfortable with the concepts of multithreading, and that's my guarantee to you. The code examples are in Java, however, most of the concepts should be transferable in other languages as well which support multithreading in some capacity. So with that in place, let's get started. So what is the motivation for multithreading? By default, programming languages are sequential in nature. Code execution happens line by line in a usual scenario. Consider the below code. So in this method, we have initDB call, then we have download data call, then we have process on data, and then finally show the results. So in a usual scenario, all these things will be executing one by one. So first this will be called, then this will be called, then this, then this. But we have a problem. In a single threaded program, these instructions will be executed one by one, and the time consuming section of the code can freeze the entire application. What is the solution? Well, figure out the time consuming tasks and decide if they can be run separately. If yes, run such tasks in separate threads. Let's have a quick layman explanation of how a time consuming step in your code can slow down or freeze your entire process. Let's say you invited your friend over to your place to watch this super cool movie. Being a great host, you decided to make some popcorn for your friend. But here is the catch. It will take some 5 to 7 minutes to prepare the popcorn. During the time you are involved in preparing the popcorn, your friend asks, which movie are we going to watch today? Since you are super involved in making the popcorn, you don't respond. Your friend, even though feeling a bit weird about the situation, asks you again if you are okay, but thanks to your involvement in the process of making the popcorn, you don't respond. Situation becomes super strange. However, your friend tries one final time and asks you if there is something wrong. And thanks to your deep dedication in the process of popcorn making, you don't respond. By this time, your friend gets freaked out and punches you in the face and you reboot. But we all know this does not happen in real life unless you are playing a prank. We humans are naturally equipped to multitask. In this example, since you would be aware of the time it takes to prepare popcorn, you would probably prepare the recipe and put the pot on the stove and let the popcorn get prepared. While it's getting prepared, you are available to do anything if there is a need. So you figured out the task which is going to be time consuming, started its execution and let it finish in its own line of execution. Effectively, you did not block other tasks on you and did not freeze entirely. If you follow line by line execution of tasks in your program, this kind of freezing situation may arise in your code if there is a task which takes longer time to execute. So what is the improvement? So in this case, let's go through the different calls. So initDB is where you are initializing certain DB related things. Then you have download data, then you process the data, then you show the results. So to me, it looks like downloading of the data is something which could take the major chunk of time. What we can do now is put this download data in some sort of other thread and everything else in some other thread. And in that sense, we can do a parallel processing, and it will ensure that by the time we are waiting for downloading the data, everything else is not getting frozen up and our system is not lagging. So this is one such improvement we could do by the virtue of multithreading. So to give it a formal definition, multithreading is the ability of CPU to perform different tasks concurrently. Now let's have a quick explanation around concurrency versus parallelism. Concurrency is like having multiple tasks to do, but you only have one set of hands. You switch between the tasks, doing a little bit of each one at a time. If you play a guitar, it's similar to that, where you play different notes and chords using your 9 fingers. Even though you play each note separately, the switch is so fast and smooth that overall it appears as if everything is being played together. Parallelism, on the other hand, is again having multiple tasks, but now you have many friends to help you out. Each friend works on a different task at the same time, so all the tasks get done faster. So in summary, concurrency is doing multiple things all at once by quickly switching between the tasks, and parallelism is doing multiple things at once by having different parts of the task being done simultaneously by different entities. Now let's learn about concurrency versus parallelism in somewhat more technical terms. So concurrency and parallelism are two terms which are used quite a lot, and that too interchangeably while discussing multithreading. But there is a subtle difference. Let's talk more about it. Concurrency refers to the ability of a system to execute multiple tasks at the same time or nearly overlapping times, so they seem like being executed at the same time. In concurrent systems, tasks may start, execute, and complete independently of each other, but they may not necessarily be executing simultaneously at any given moment. Concurrency is often achieved through techniques like multitasking, where a single processor switches between executing multiple tasks rapidly, or through the use of multiple threads or processes. Parallelism, on the other hand, refers to the simultaneous execution of multiple tasks to achieve faster performance or increased throughput. In parallel system, tasks are truly executed simultaneously, either on multiple processors or multiple processor cores, or through other means of parallel processing like distributed computing or GPU computing. Parallelism is all about breaking down a task into smaller, non-related subtasks which can be executed concurrently to speed up the overall execution time. Thus, in the context of a hardware with a single CPU core, concurrency could be understood as a perceived parallelism or fake parallelism, even more so in scenarios where tasks appear to be running simultaneously but are actually being executed sequentially or in an interleaved manner. This is done by something called as time slicing algorithm. So in summary, concurrency is about managing multiple tasks or processes, potentially interleaving their execution to give an appearance of simultaneous execution, whereas parallelism, on the other hand, is about truly executing multiple tasks or processes simultaneously to achieve a faster performance. While the terms are related and often used together, they refer to distinct concepts in the context of computing. Now let's understand what is a process and thread. Process is an instance of program execution. When you enter an application, it's a process. The operating system assigns its own stack and heap area. Whereas thread is a lightweight process, it is a unit of execution within a given program. A single process may contain multiple threads. Each thread in the process shares the memory and the resources of the parent process. One single process could contain many other threads. Now let's learn a bit about the time slicing algorithm. Let's imagine we have multiple threads associated with a process. Somehow the CPU has to ensure that all these threads are given a fair chance to execute. One such approach is to use the time slicing algorithm. So uses time for the CPU is shared among the different threads. So here is what happens. So you see, sharing is time slicing. Let's say the green boxes represent one thread and the yellow boxes represent another thread T1 and T2 respectively. And consider that this is the timeline, and at this particular time thread T1 is assigned to the CPU. Then after some time thread T1 takes a break and we assign thread T2 to the CPU, and after some time T2 is given some rest and thread T1 is assigned again to the CPU. So as you see, it's going into a back and forth manner where each and every thread is taking turns to run on the CPU one by one. So here what we are doing is we are basically slicing the time and we are assigning certain time quantum to the CPU. So here we have a CPU, and these are the two different threads which are kind of taking its turn to be executed on the CPU. So this is how the time slicing algorithm works. Now what happens when we have enough CPU at our disposal? So let's say we have thread 1 and we have thread 2 and there are two CPUs. So in that case, thread 1 will run entirely on CPU 1 and thread 2 will run entirely on CPU 2. So it's effectively a parallel kind of processing wherein we are not sharing anything on a given CPU. Rather, each thread has a dedicated CPU and it does not need to bother about whether it has to share the CPU with the other thread or not. And please note that I have put CPU here, but it could be a different core in the CPU itself. So it could be either different cores of a given CPU or it could be different CPUs. So that depends on the hardware. In such kind of setup, we can achieve the parallel processing. Now let's look at some of the pros and cons of multithreading. The first one is we can build responsive applications. So now you don't have to worry about freezing situation, and thus you can build your applications to be responsive. Second is you will have a better resource utilization, because now with the use of multithreading you could ensure that your hardware or your CPU is not sitting idle. Rather, once it's idle, it could be taken up by some other thread for execution. And the third thing is it helps us into building performant applications. So with the help of multiple core CPUs, we can build parallel programs, and essentially we could get some benefit on the side of performance as well. Now coming to the cons of the multithreading, the first one is synchronization needs to be done and it can get tricky at times. So essentially when you are doing multithreading, you need to share the memory space and other resources with a process. And in that case, let's say when there is a process and there are certain number of threads, you need to share the resources. So we need to ensure that we are not running into funny situations. And those things are handled by something called as synchronization. We will have a much more focused discussion around all these things later in the video. The second thing is it is difficult to design and test multithreading apps. So essentially you don't have a control in which the different threads could execute. So in that sense, it's difficult to predict the behavior of the threads. So it's difficult to design and test multi-threaded applications. And the third thing is thread context switch is expensive. So if there are more than required number of threads, then it becomes detrimental to your system performance. So multi-threading is not a silver bullet which will help you with all the situations. Rather, we should use it judiciously. Now let's have a look on the thread lifecycle. Any thread will start its lifetime in the new state, and every thread is in this state until we call start on it. After we have called a start on it, it goes to something called as active state, and this active state has two substates. Either it could be runnable or running. As we saw in the earlier slides, in some cases we may have to do some sort of time slicing. Then in that case, there could be 5 threads which are ready to run, but there is no CPU available on which it could run, and we have called a start on such threads. So those threads will be in runnable state, and there could be certain threads which will be in running state. And as soon as those running state threads are done, then they could allow the threads in the runnable state to run again. And this is what we mean when we say that it has two substates, which is runnable and running. Effectively, this is the active state. And the third state is the blocked state. So every thread is in this state when it is waiting for some thread to finish. So let's imagine there are two threads, T1 and T2, and then they both started running on the CPU, and after some time T1 got a chance and it was executing its task. After some time it had to be taken out of the CPU and T2 got a chance. But now T1 is not completed. It's waiting for its execution to complete because T2 is now on the CPU. So T1 is in a blocked state, and this is what we mean by the blocked state. Now T1 will get a chance to execute on the CPU, and maybe it may be done with its entirety of execution, and then it goes to a state called as terminated state. So every thread is in this state after it's done doing its required task. Here we are in the IDE. I have created a normal Java project and it's called as multithreading. So the plan is that for the entire duration of this tutorial, I'll be using the same project and I'll be creating different packages inside the project to discuss the concepts of the multithreading. So in this particular section, we will be discussing about the sequential execution. So in order to demonstrate the code, let's create a class, call it a sequential execution demo. And here is the idea behind this particular class. I will be creating certain methods, and the intent of this particular class is to showcase that in a normal Java program, the execution happens line by line and there is no jumping around from this part of the code to the other one. So let's get going. So to begin with, I'll create the main method, and in the main method, I will have two methods. Let's call those as demo1 and demo2, and let's create those two methods. I won't be doing anything fancy. I'll just create a normal for loop which will be iterating in certain range, and then it will print some message, and that's it. So let's copy this one and let's change the name, and here let's change the message as well. And now let's run the program. On running this is the outcome that we have. So first we were executing demo1 method, so the entirety of demo1 is executed, wherein it will be printing from 0 to 4 with this message, which is from demo1 plus I. So from demo1 0, from demo1 2 till 4, and likewise we have executed demo2, and in that case we print this message, which is from demo2 and the ith number, which is from demo2 0 to from demo2 4. So what we see is that the execution happens line by line. So the main method is the first one to get started, and the first thing it sees is that we are invoking a method called as demo1. It goes there, it executes it, it comes back. Then the next line it says is that it's demo2. It goes to demo2, it executes it, and it comes back here, and then the execution terminates. So this is what we mean by the sequential execution. So in the context of multi-threading, what we can understand is that each and every program is single threaded unless otherwise instructed. So here we just have a single thread, and that is the thread that is created by the JVM for the execution of this main method. And this could also be called as the parent thread or maybe the main thread. Now let's learn about the way in which we can create threads in Java. And the first way is to implement a runnable interface. So we will create a class, let's call it as runnable thread example, and let's have a main method created. The way it works is that we will have to define some sort of class, and the class will implement a runnable interface. So let's do that. So let's call it as thread1, and it will implement the runnable interface, and the runnable interface has one method which we need to implement. So that's run method, and the logic is whatever we implement inside the run method, that is executed by this thread. So let's do that. So let's have a for loop which runs from I0 to I4, and it prints a message. Let's call it as thread1, and I would be the ith time it has been called. Now let's create another thread. Let's call it as thread2, which implements runnable, and let's implement the run method. And here as well we can run from I0 to I4, and let's print the message, call it as thread2 and I. So this is a way in which we can define the threads, and once the threads are created, they need to be somehow started. So in order to do that, what we can do is we can define a thread. Let's call it as 1, then new thread, and we can pass the class that we have created. So thread1, and likewise we can say thread2, new thread 2, and we have the handle for these two threads 1 and 2. So how do we start these threads? Well, we have a method called as start. So let's do that. So what happens is, once you call the start method, JVM will start these two threads and they are in the runnable state. So they could be either immediately running or they will have to wait because they don't have any CPU available at their disposal where they could go and run. So let's run this and see what is the outcome like. So what we see here is first thread 1 is running, then we have thread 2 running, but this may not be the case always. So in order to see a clear example, let's increment the number of times we are going to print this message. So let's increment it to 10 and let's do this to 15. Now let's run the program and see the outcome. So here is what we see. First we have thread 1 running and then thread 2 takes over. And then thread 1 is running and then thread 2 takes over. And so on and so forth. So once everything is executed, the execution will stop and the program will terminate. So what we are observing is we have created two threads, we have started the threads, but there is no sequence in which they are executing. Rather, the thread has been created and it's available to be scheduled by the thread scheduler, and once the thread scheduler finds an available spot for a particular thread to be run on the CPU, it's assigned to the CPU and that's the time it's running. For the time when it does not have the access to the CPU, the thread will have to wait. And that is the reason we are seeing a back and forth execution pattern wherein first one thread will run for some time, then thread 2 will take over, and then thread 2 will wait for some time, and then thread 1 will take over. There is also a different way in which we can create a thread using the Runnable interface, and that is by making use of the anonymous inner classes. So let's create thread 3, then new thread 3, and what we can do is new Runnable, and let's print a similar kind of message. So I less than, let's say 15, I plus plus. The message could be thread 3 plus I, and we can do the same thing, which is 3.start, because 3 is the handle that we have given for this particular thread. One thing which you can observe is that this could be easily turned to a lambda. So let's do that. And here we have a much cleaner way of creating a thread using the Runnable interface. So all we need to do is inside the lambda, we can provide the logic which needs to be executed by that particular thread. Now let's run it and see its outcome. So we can see thread 2 is running, then thread 1 is running, then thread 3 is running, and every thread gets some time of execution with the CPU, and eventually all the threads are executed and terminated. So this is how we can create threads in Java by implementing the Runnable interface. The other way of creating a thread in Java by extending the thread class with the help of extends keyword. Let's learn about the same. So let's create a class and let's call it as extends thread example. Let's create the main method, and now let's create the different threads. So let's call it as thread1 extends thread class, and likewise we had to override the run method in the example of Runnable approach. We need to do something similar here as well. So let's do that. And we can have a for loop which runs from I as 0 to 9, prints a message. Let's copy this. Let's call this thread 2. Let's change the message as well. So we have created two threads, which is thread 1 and thread 2. Now we need to instantiate it. So let's call this as thread 1 and then new thread 1, then thread 2 and new thread 2. Please note that here we are directly creating the thread class. We are not passing this object inside the thread constructor like we were doing in the case of Runnable approach. So now once we have the handle for the threads, we can call .start on these two. Let's run this method and see the results. So what do we see? we have thread 1 running, then thread 2 takes over. Now again we have thread 1 and then thread 2 takes over. Finally everything is executed and the program gets terminated. So the basic idea remains the same. Once we call .start on these threads, they are in the runnable state, and based on the availability of the CPU, they will be submitted to one CPU and they could start with their execution. Now that we have seen both the approaches of creating a thread, one by implementing the runnable interface, other by extending the thread class, let's see which approach is better. So if we extend thread, then we cannot extend any other class. Usually it's a big disadvantage. However, a class may implement more than one interface. So while using the implements runnable approach, there is no restriction to extension of class now or in the future. So in most of the cases, runnable is a better approach to create a thread. Now let's learn about .join method in Java. Let's create this class. Let's call it as join thread example. And first we create the main method. Let's create thread 1 and we can use the anonymous inner class or maybe lambda to create the thread. So this thread is going to print from 0 to 4 and it will have a message. Call this as thread 1 followed by I. Let's copy this one. Let's call this as thread 2. Let's change the message as well. Now thread 2, and this is going to be printed for, let's say, 25 times. And first we call .start on the 1, then we call .start on the 2, and then let's have a message which says done executing the threads. So what do you think is going to be the output for this particular program? If you are new to multithreading, then you could say that first these two threads will be executed and we will see all these messages getting printed on the console, and finally we will have this message printed. But looks like it's not going to be the case. So let's run it and find it out. And definitely it's not the case. In fact, done executing the threads is the first thing to get printed on the screen. So why is it happening so? In order to understand this, we will have to take a step back and understand how does the main method works. So in this particular program, main method is the first thing which is getting called by the JVM. And when this happens, this main method is run by a main thread. So this main thread is the first one which gets assigned to the CPU with the highest priority. We will learn about priority and all those things in some time, but for now understand that this main thread has the highest priority. So it starts with its execution. First thing it does is it creates the definition for thread 1. Second thing it does is it creates the definition for this thread 2. And it comes to line number 17, then to 18, and in these two lines it moves these two threads in the runnable state. And finally on line number 19 we have this message. Since the main thread has the highest priority for now, this message is printed first. So what happens is all these threads are executing independent of each other. So thread 1 will start with its execution independently, so will thread 2, and the main thread anyway has the access to the CPU for now. It's going to print this one as soon as possible. And that is the time it's done with its execution, and it waits for these two threads to complete their execution. And once that is done, then the program is going to terminate. So what should I do if I have this functionality wherein I want that thread 1 should be completed, and only after that happens the main method or the main thread should proceed with its execution? So in order to implement that functionality, I can make use of .join method. So let's call .join on thread 1, and .join method throws an interrupted exception. In order to correct this, we can either surround this with try catch or could add the exception being thrown in the method signature itself. I'll go with the second option. Now with this in place, let's run the program and see what is the outcome. So this is what happens. Thread 1 needs to be executed 5 times and thread 2 needs to be executed 25 times. So first thread 1 is executed, 1 is getting executed, and looks like by this time thread 1 is executed. And at the same time thread 2 got hold of the CPU, so it started executing. And you notice that for the next time thread 1 was supposed to be executed, but thread 1 did not have anything left for execution. Effectively, it was done with its execution. And that is where the dot join came in effect, and it instructed to the JVM that one is done with its execution. Now it's time for the main thread to take over and proceed with its execution, which is printing this particular line. So now we print this line, and then thread 2 proceeds with its execution. It's going to print all the messages by thread 2. And as soon as this is done, both the threads are completed, and now the main thread also shuts down. So what we learned here is one.join is kind of hinting to the JVM that as soon as I am done with my execution, then you can start with the execution of other threads which are in the queue. In this case, we had 2 and the main thread. So first 2 was executed for a while on the CPU, then the main thread started with its execution, which was printing this line. So what happens if I place 2.join as well? So in that case, JVM will not only wait for the thread 1 to get completed, rather it will also wait for thread 2 get completed, and only after that this message will be printed. So let's try that out as well. Let's rerun the code and see what is the outcome. So you see all the threads are executed. So basically 1 and 2 are finished, and only after that we see the outcome, that is done executing the threads. Now let's print a message before executing these threads, and what we can say is before executing the threads. Now let's run it. So you see, first we see the message before executing the threads. Now all the threads are executed because we have placed .join on both of these two, and finally done executing the threads is being printed. So basically why this is happening is, till this point of time we have not put the threads into the runnable state. So the main thread is the only active thread in this context, and this is the reason we printed this as soon as we reached at this line. So now let's understand about the join operation with some theoretical concepts. So first thing to notice is that main thread is the parent thread. So when we start a program, usually the execution begins with the main method. This method runs on the main thread. This can be understood as the parent thread since it spawns the other threads as well. Then the other important point to notice here is the independent execution of threads under normal circumstances. So when you create and start other threads, they run concurrently with the main thread unless instructed otherwise. So under normal circumstances, all threads run independent of each other. More explicitly, no thread waits for other thread. So what is join method? Well, imagine threads to be lines of execution. So when we call .join on a certain thread, it means the parent thread, which is the main thread in this case, it's saying, hey thread, once you are done executing your task, join my flow of execution. It's like the parent thread waits for the completion of the child thread and then continues with its execution. And here is my perspective on this concept. Well, personally, I find the join keyword is not very intuitive at first for the kind of operation it's doing. Somewhat better terms could have been wait for completion or complete then continue. What's your perception about the join method in Java? Let me know in the comment section. Now let's learn about the concept of daemon and user threads. On the basis of surface of execution, threads can be of two types: daemon threads or user threads. Daemon threads usually run in the background, wherein user threads are the active threads. So when a Java program starts, the main thread starts running immediately. We can start children threads from the main thread. The main thread is the last thread to finish its execution under normal circumstances, because it has to perform various shutdown operations. Daemon threads are intended to be helper threads which can run in the background and are of low priority. For example, garbage collection thread. Daemon threads are terminated by the JVM when all other user threads are terminated or they are done with their execution. So under the normal circumstances, user threads are allowed to be terminated once they are done with their execution. However, the daemon threads are shut down by JVM once all the other threads are done executing. Now let's have a quick code demo for the concept of daemon threads and user threads. So let's create this class called as daemon user thread demo, and first of all we will create the main method. Now let's create two threads. First is daemon helper implements runnable. Let's override the run method. The second thread is user thread helper implements runnable. Let's override the run method. Now let's write the code which needs to be executed by the daemon thread. Let's have a counter variable, start with 0, and while count is less than 500, do a thread.sleep and then do a count plus plus. Finally print this message, which is daemon helper running. The sleep will expect us to pass certain time. Let's give the time for 1000 milliseconds, and the sleep method throws an interrupted exception. So let's surround this with try catch. For the user thread method, let's have a sleep timer for, let's say, 5000 milliseconds, and let's surround this with try catch. Then print this message, user thread done with execution. Now let's create these threads in the main thread. So first we start with the daemon thread. Let's call this as a background thread, that is busy thread. So new thread, new daemon helper. For the user helper, maybe we can call this as user thread, new thread, new user helper. By default, any thread is not a daemon thread. The way to make a normal thread as a daemon thread is by calling .setDaemon method. So let's do that. Busy thread .setDaemon and true. Finally, we will start these two threads. So busy thread.start and user thread.start. Now let's run this program. So here is what happens. The user thread has a sleep timer of 5 seconds. So as long as the thread was started, it got assigned to the CPU, and once it was assigned to the CPU, it went into a sleep stage, and then the daemon thread was assigned the CPU. And during that time, there was no thread which was contesting for the CPU, so the daemon thread kept on running in the background. So it ran for 4 seconds. So remember, we had the sleep timer for 1000 milliseconds. So after every second, this was running and printing the message daemon helper running. As soon as the 5 second got completed, this thread came back into existence and it printed user thread done with execution. And once this happened, then the user thread helper got concluded. It got finished with its execution, and now what JVM sees is that there is no other thread which needs to be executed. So by this time, all the user threads, which is basically just this thread, is done with its execution, and now it's time to shut down the JVM. And that is where, even though this daemon thread was not completed, because in the normal case of operation, it could have ran till the count was less than 500, which was certainly not the case because it ran just for 4 times, but still it was terminated because the user thread was terminated. So this is what we learned from this particular demo, that user threads are given the priority, daemon threads run in the background, and once all the user threads are concluded, the JVM shuts down the main thread, and along with that, the daemon thread is also forced to be shut down. Let's learn about a very important concept of thread priority. So let's say there are 10 threads in runnable state, however there is only one available CPU, so only one thread can execute at a given point of time. Others will have to wait. So who decides which thread gets to run on the CPU? Well, the component who decides this is called as the thread scheduler. So each thread has a certain priority to begin with, and under normal circumstances, the thread with the higher priority gets to run on the CPU. Please note the keyword under normal circumstances. The priority value varies from 1 to 10 and it can be assigned to any thread. 1 priority is represented as the min priority and 10 priority is represented as the max priority. By default, the priority of a thread is 5 and is represented as norm priority. Norm as normal. Threads of the same priority are executed in FIFO manner. So the thread scheduler stores the threads in a queue. Now let's just spend some time to understand this part of normal circumstance. So what happens is all the main threads are started at a normal priority of 5, but still they are privileged to be executed first on the CPU by the thread scheduler. Why so? Well, it's by design. Since it's a main thread, it has to be executed first, otherwise your program will have to wait unnecessarily. So this is the first thing which gets to be executed in any case. Even though the priority of the main thread is 5, it gets the first priority to be executed on the CPU for the first time. Now let's have a code example to have a demo of the thread priority concept. So let's create this class called as thread priority example. Let's have a main method. We can get the priority of the current thread by calling thread.currentThread.getName. So let's print this out. Now let's get the priority of the current thread. So we can call thread.currentThread.getPriority. Let's print this out as well. Now let's get the current thread. So thread.currentThread.setPriority, and we have thread.maxPriority. Let's print the updated priority. Let's run this. So the outcome we will expect is the name of the main thread, then the current priority, which is the default priority because we did not change it earlier, and after we change it, what is the priority. Let's run and find out. So the name is main to begin with. The default priority is 5. We updated the priority to maximum and then we printed the same. Let's print something. So thread.currentThread.getName says hi. Now let's create one thread. Say thread1 says hi as well. And by default, the new thread, which is thread1, will have default priority of 5. Now let's give this the maximum priority possible, which is thread.maxPriority, and then 1.start. So what do you think will happen? Now that thread1 has the maximum priority and the main thread is still at the default priority of 5, I should expect that this one should be executed first. Then I should see the outcome for this one. So let's run it out and see what is going to happen. Well, what we see is the first one to get executed is main says hi, then the second is thread1 says hi as well. So please note that this property of main thread getting the first priority or the higher priority to get executed on the CPU, regardless of this having the lower priority, which is 5 as compared to the max priority, is only for the first time this thing gets executed. Once the execution starts, it will go by the FIFO manner, and then the thread scheduler will schedule the threads based on their priority, and if they happen to be of the same priority, FIFO will be used to schedule the threads. So this is how we deal with priority in the case of threads in Java. Now that we have learned the basic concepts of multithreading regarding how we can create threads and how we can wait for threads to complete using the join keyword, etc. Now it's time to learn about the important concept of thread synchronization. So let me create a package to write the code. So let's call this as thread synchronization, and I will implement a class. Let's call this as synchronization demo. So here is what I want to implement in this class. I want to have a counter variable that will be initialized with 0, and I will be using 2 threads to increment this number up to certain times, and in the end I will check the final value of the counter variable. So let's do this. So first thing is, let's create the main method, and let's have a counter variable as well. Let's call this as private static int and counter. Let's initialize this to 0. Let's create 2 threads. So as seen in the earlier video that we can create threads in line using the lambda expression. So let's do that. And in this thread, what I want to do is that I want to increment the value of counter, let's say 10,000 times. And let's call this as counter plus plus. Let's do the same using another thread. So I have a code template that I could make use of. So that will save me some time to type the code. Again, let's have this for loop run 10,000 times. And those many times we will increment the counter variable. Then in the last, what I will do is I will start these 2 threads. So let's name this as 2. Oops. And 2.start. And before printing the final value of the counter, I want to make sure these 2 threads are completed. So the way to do is I would call join on this. So let's surround this with try catch. Let's duplicate it and let's call the same for thread 2 as well. And finally we could print the counter value. Now let's run this one and see what is the outcome like. So let's run this and see the output. So the output that we have is 16,583. But what we expect ideally is that since this thread is executing it 10,000 times and this thread is running this for 10,000 times, then effectively it should have been 20,000, right? But that is not the case. What we are having is 16,583. How about let's run it one more time? And this time we are getting a totally different number. Let's run it one more time and we are getting a totally different number. So this is not correct, right? Then how can we correct this? So even before we learn how can we correct this, it makes sense to learn why this is happening. So the reason for this behavior is something called as a non-atomic operation. So what exactly is a non-atomic operation? Well, what we see here is we are incrementing the counter variable. Counter is counter plus 1. Even though it appears as if the counter variable will be incremented by 1 in one shot, but that is not the case under the hood. Under the hood, what will happen is first the counter variable will be loaded in the memory, then it will be incremented by 1, then this will be assigned back to the counter variable which is holding this particular value, and that is where we set the variable value back to counter plus 1. So essentially this is consisting of 3 steps. So the first step you could think of it as load, second step is the actual increment, and then set back the value. So let's say at this point of time thread 1 starts operating on this particular logic which is incrementing the counter variable. Let's say at that point of time the value is 0 and it incremented the value. The incremented value became as 1 and now it's time to apply this value, incremented value, back to counter variable. But at the same time thread 2 came into the picture and what it did is it said, hey, let's load the value for counter, and it found that the counter value still is 0 and then it went ahead. So let's call this as this being the operation by thread 1, and now thread 2 came into the picture. It said, hey, let's load the value for counter, and it is 0, and what I'll do is I'll increment the value. So after incrementing the value it became as 1, and this is where we have thread 2 doing this operation. So effectively this value should have been 2 by this point of time, but unfortunately, since the time at which this thread 1 could have set the value as 1 and applied that value back to the counter variable, and that is where the thread 2 came and it intercepted the execution, and it found out that the value was 0, it incremented it back to 1. What should have been a 2 here, that is still 1, right? So this is the inconsistency, and this is the inconsistency due to which we are seeing this error, that we are not getting the final value of 20,000 here, rather we are stuck at some lesser number. So what exactly we call this phenomenon? Well, so this thing is called as race condition in the terminology of multithreading and concurrent programming. So what we have here is a shared resource, that is the counter. We have two threads working on the same shared resource, and these kind of scenarios lead to inconsistencies which are called as the race conditions. So how exactly can we fix this? So the way to fix this is, if you have different counters on which these two threads could work on, then probably this could work on one counter, this could work on another counter. But that is not the case here, right? The whole point of discussing this example is that we have a shared resource and we want to make use of multithreading concept to have some sort of operation applied to this particular shared resource. So in order to avoid this kind of situation, what we can do is, we could somehow ensure that this operation, right, this operation is being done by one and only one thread at a given point of time. So that way what we could achieve is, this is not being done simultaneously at the same time by two threads, and in that sense we could achieve something called as mutual exclusion, and it will ensure that once thread 1 has the access to this particular logic which is incrementing the counter, then it will do all the three parts, which is loading the counter, incrementing the value, and setting back the value to counter. So now counter has 1, and once thread 1 is done with its execution, then the other thread could make use of this particular shared resource in its own execution. So essentially we are restricting the uses, the access to the shared resource by multiple threads at a given point of time. And how can we achieve this? So one way to achieve this is with the help of keyword synchronized, and we could do this at multiple levels, like have this synchronization at the method level or the block level. So now let's see how can we fix this using the synchronized keyword. Create another method, and let's call this as increment, and what this will do is, it will simply increment the counter variable. Let's replace this counter plus plus with this increment. Let's do the same here as well. And what we have here now is a method which is going to increment the variable. And as I told earlier, that we want to ensure that this particular operation is being called by just one method at a given point of time, what we can do is, we could restrict its access. And the way to do this is put a synchronized keyword here. So essentially, by uses of the synchronized keyword, what we are saying that, hey JVM, please allow this particular method to be accessed by just one and only one thread at a given instant of time at any cost. And that is how we have achieved synchronization in our code. So this thing is also called as critical section. So one way to understand this is that this section is quite critical to the execution of the program in the context of multi-threaded environment. So we are limiting its access or the uses by one and only one thread at a given point of time. So with that in mind, let's go ahead and run the code and see what is the outcome like. So let's run this. And now we can see that we are getting the exact value of 20,000. Let's run it a couple of more times. And each and every time we see the value remains to be 20,000 itself, and there is no changes as such. So it feels like we have fixed the issue of synchronization by using this synchronized keyword. But there are a few inherent problems with this particular approach. The approach that we are talking is using the synchronized keyword at the method level. So in order to understand what are those problems, let's first understand how does the synchronized keyword work in Java. So first thing is, let's understand the monitor locks. So each object in Java is associated with a monitor, which is a mutual exclusion mechanism used for synchronization. So when a thread enters a synchronized block or a method, it attempts to acquire the monitor lock associated with the object on which the synchronization is applied. So imagine that there is a shared room. That room could be used by just one person at a time. Then you have to enter inside the room using some sort of lock. You use the lock, you open the door, you go inside, and then once you come out, you release the lock. You hand over the key to someone else who wants to make use of the room next. Likewise, in every Java object, we have this monitor lock, which is also sometimes called as the intrinsic lock, which needs to be acquired by the thread which wants to make use of the synchronized block or the synchronized method or the critical section. When a thread enters the synchronized block or method, it attempts to acquire the monitor lock, and if the lock is available, the thread acquires the lock and proceeds to execute the synchronized code. So what do we mean by the lock is available? Well, what it means is no other thread will be currently holding that lock. So if the lock is not available, that is another thread is holding that lock, then the thread enters a blocked state and it has to wait until the lock becomes available. The second step of this process is releasing of the monitor lock. So when thread exits, let's say the thread is going to exit after this execution is completed, it has to release the monitor lock, and thus it allows other threads waiting for to acquire the lock and to proceed with their execution. So the monitor lock used by the synchronized keyword is sometimes referred to as the intrinsic lock or the monitor lock of the object instance. Each object in Java has its own intrinsic lock, and the synchronized keyword acquires and releases this lock implicitly when used at the method level or in the synchronized block. So what is the problem exactly if we use this synchronized keyword at the method level? So the first problem is that it's a kind of coarse-grained locking. So when we use synchronized at the method level, it applies the lock to the entire method body. Even though in this case our method body is just a one line, but in actual code base it could span to multiple lines. So essentially what you are doing is you are blocking any other thread from entering that particular method when you have applied the synchronized block on that particular method. But your critical section could be just 2 or 3 lines. So in that sense, it does not make sense to block an entire method which could probably, let's say, have 30 or 40 lines, right? So that is the first problem with using the synchronized keyword at the method level. And needless to say, this leads to reduced concurrency and performance bottlenecks. And the second thing is kind of related to the first issue itself. So when synchronized is used at the method level, we lose the fine-grained control needed in the more complex scenarios. So for example, you might want to synchronize only a specific section of the code within the method, or you might need to synchronize multiple methods together as an atomic operation. Using method level synchronization, you don't have this granularity level. And the third issue is, let's say when a subclass is overriding a synchronized method from its superclass, it must also explicitly declare the method as synchronized if it wants to maintain the synchronization behavior. And the failure to do so can lead to unexpected behavior and potential synchronization issues. So you see, there are multiple issues with the synchronized keyword when we use this at the method level. So let's understand this with some code example. In the same code, let me do some refactoring. Let's call this as counter1. Let's create another variable. Let's call this as counter2. And let's call this as increment1 and this as increment2. And what we can do next is we can duplicate this method and let's call this as increment1 and it's going to increment the counter1. Let's call this as increment2 and it's going to increment the counter2. Let's print these values in the last. So counter2. So from the functionality perspective, it's surely going to work fine. So counter1 will be 10,000 and counter2 will be 10,000. Let's run it and confirm. Yeah, this is working fine. Let's rerun it a couple of more times to ensure that it's working as expected. So it's working fine, but there is a problem. So if you look closely, what we have done is we have used the synchronized at the method level. So let's say thread 1 starts working, and at that particular point of time increment 1 is getting invoked. So thread 1 has acquired the lock to this particular code, this particular method, and it's working on counter 1. But if you notice, thread 2 has no business with counter 1, right? Because it's going to operate only for incrementing the counter 2. So in this case, even though thread 2 is not directly working on counter 1, it will be blocked because this synchronized behavior is going to acquire the class level lock. So this is the class level lock. For this particular class, there is only one lock, which is this intrinsic lock or the class level lock or the monitor, and that is acquired or held by the thread 1. And in that sense, thread 2, even though it was not supposed to be blocked, it's blocked now. So I think you see the problem now, and that is one major problem with the synchronization at the method level. So to address these concerns, it's often recommended to use explicit locking with synchronized blocks, or to use more flexible concurrency utilities provided in the Java util concurrent package, such as lock interfaces, reentrant locks, read-write lock, etc. And we will be learning all these things going forward in this tutorial. But for now, let's understand how can we fix this scenario by the uses of custom locks. So let me create another class. Let's call this as lock with custom objects. So first of all, let's have the counter variables. So private static int counter 1 as 0. Let's duplicate this. Let's call this as counter 2, and let's have the main method. In the main method, we will have two threads. So let's call this as thread 1, let's call this as thread 2, and this will be incremented for 10,000 times. Let's call the increment 1. Let's copy this one and let's rename this to increment 2, and let's start the threads. So 2 dot start, and let's wait them to complete their execution. So in catch we will have interrupted exception, maybe call this as E, and then we want to throw a runtime exception. Let's call 1 dot join, and then 2 dot join, and let's print the value counter 2. What we want to do now is we want to implement the increment methods. So increment 1, and this time we don't want to have the synchronized keyword at the method level. Rather, where we want to place this is at the block level, where we want to do the synchronization. So this will be counter 1 plus plus, and if you notice, when we place this at the block level, it's expecting us to pass something. What does it expect us to pass? Well, it expects us to pass the lock on which we want to lock this critical section, so that two different threads for this particular critical section cannot enter in this code block. So the way we will do it is that we will define two locks. So let's call this as private static final object lock 1 new object, and let's do for lock 2 as well in the similar manner. And now we can have this on lock 1. So let's duplicate this, and let's call this as increment 2 and increment 2, right? So basically what we have done is that we have the increment 1 method and then increment 2 method, and these two methods are supposed to work for two different variables, counter 1 and counter 2. And since these two methods are being used by two different threads, and moreover these two methods are working on two different shared resources, not the same one, which is counter1 and counter2. We want to lock it on two different locks. So basically for this critical section, if you want to acquire this particular area, you have to access lock 1. If you want to acquire this particular area, you have to access lock 2. And this is how we have decoupled, we have separated out the concerns for these two different threads, thread 1 and thread 2. So this is how we make use of the synchronized keyword at the block level and fix the issues with the users of synchronized keyword at the method level. But having said so, it's not a rule, rather it's just a guidance or a general opinion. But if in your case, if your method happens to be quite a short one and does not have any other implementation, and moreover, let's say the entire method block is itself the critical section, then in that case, you can go ahead with the method level synchronized keyword as well. But more often than not, this is not the recommended approach. Rather, you should explore the option of going with the synchronized block itself. Now that we have seen the concept of synchronization, it's time to understand a very important concept of wait and notify. So before we start with the concept of wait and notify, let's see what we have on the screen. So let's imagine there is a room and the room always contains some sort of parcel, and the catch here is that the parcel could belong to anyone. So let's say there are 4 or 5 people and their parcel is getting delivered. So you need to go inside the room and then take out that parcel. But the room is locked and there is a security who is there on the room entry, and the only way to access the room is to get that lock from the security. Once you have the lock, you can go inside the room, fetch your parcel and come out. But here is the catch. At a given point of time, only one person is allowed to access the room. Everybody else will have to wait. So how this can be implemented? So the way it could work is that once the security is giving a lock to anyone, they will allow them to go inside and fetch their parcel. And till the time whosoever is coming to access the room, the security could tell them that somebody is already inside the room, so you will have to wait till that person comes out. So once the person who is inside the room gets his parcel, he comes out and he hands the lock back to the security. Now the security will notify that the room has been vacated by the earlier person, and anybody else who was waiting for the room to access it could go inside and get their parcel. But again, they will have to ask the security for the access to the lock, and then they will open the lock and then they will go inside the room to get their parcel. So you see, there is a mechanism which is kind of allowing just a single person entry inside the room in order for them to do something inside the room, which is the activity of collecting their parcel. Until the time anyone is inside the room, the entire room is considered to be frozen or kind of locked, and nobody could access it. And as soon as that person is coming out, then they are handing the key to the security, and after that is done, the security is notifying to everybody else that now room is available to be accessed, and then anyone from the waiting line could come and collect it. So the wait and notify methods work in a very similar way. So when a thread calls wait on the lock, then that thread is suspended from its execution and it goes to something called as a waiting state. And when it goes to the waiting state, then others who were in the waiting state earlier, they have a chance to get hold of the lock, and then they could start with their execution. And as soon as they are done with their execution, they could call notify, and notify is a message to all the waiting threads that now whatever they were waiting for, that lock has been released, and then they could take that lock and access their critical section to work upon. So that is the whole idea behind the wait and notify methods in Java. Now we will see this with one code example and it will become more clear. So in order to demonstrate the working of wait and notify, I have created this class. It's called as wait and notify demo. So first let's start with writing the main method. Next we will create 2 threads. So let's call this as thread 1 and this one as thread 2. Let's start the first one. Let's start the second one. And let's create a lock as well. So call it as public static private static final object lock and new object. Let's have two worker methods which will be invoked by the different threads that we have created. So first one is public static void. Let's call this as 1 and it will throw an interrupted exception. Why? We will see it later. So what we will do is we will synchronize on the lock, and the first thing that we do is we print some message like hello from method 1, and then on the lock this thread is going to call wait, and then we print some message back again from the method 1, or maybe back again in the method 1 makes more sense. Let's create the other method as well. It will be called as 2. So why did we throw the interrupted exception? So when we call wait or notify, these are interruptible and they will throw an interrupted exception. That is the reason we need to have this in the method signature. So let's put synchronization on the lock, and let's have this message hello from method 2, and now this time let's call notify and let's print some message hello from method 2 even after notifying. And let's call these methods in the threads. So this will call 1. Let's add this in the try catch block. Let's call 2 here, and let's add this in the try catch block as well. And now let's try to analyze what's going to happen. So what we have done is we have created the thread 1 and it's going to make use of this particular method. So what this method is doing is, let's say thread 1 is started and after that the control comes here. So in this synchronized block, the lock has been acquired and this print message will be executed. So we will see this message on the console. Now what does this thread do is that it calls .wait. So this thread will be suspended and it will go in a waiting state since the other thread was started as well. And what this thread is doing is it is calling method 2. The execution comes here, and since wait was called, so lock was available. So this lock was acquired by this particular thread and this message will be printed that hello from method 2, and then we call .notify. So one important thing to note here is that even when we call notify, then whatever code execution is left out for that particular synchronized block, all those things will be executed. Only after they are executed, then the notify will come in effect. Other threads which are waiting for the lock to be released, they will acquire it and start with their process. So basically after notify is called, it's not that the control will go directly to this particular part, rather it will print out the remaining thing which is hello from method 2 even after notifying, and then the control comes here to this thread and then it will print this message that back again in the method 1. So let's execute this and see the outcome. So we are here, run wait and notify demo. So here is the outcome. So first is hello from method 1 and then we called wait. So it goes to the other thread, it says hello from method 2, and after notify we had another message as well. So that is getting printed, that is hello from method 2 even after notifying. Then we have the control back here which is back again in the method 1. So you may have a question that what is the difference between wait and sleep? Aren't these both same, right? So on the surface they do look quite similar, but there is a key difference that wait is used for inter-thread communication and synchronization, while sleep is used for just pausing the execution of the given thread for a specified duration. And please note that this is just one implementation of wait method. There are other implementations as well. So when you call wait with this timeout information, it causes the current thread to wait until it is awakened typically by being notified or interrupted. Otherwise, if not so, then after the time has elapsed, it will be automatically awakened. And there is another variant of notify, which is notify all. So in the case of notify, it makes up a single thread, but in the case of notify all, it notifies all the waiting threads that are waiting for a given lock. So this should be it for the introduction of wait and notify methods in Java. Now let's go ahead and make use of it to implement the producer and consumer problem. So what is producer consumer problem? The producer consumer problem is a synchronization scenario where one or more producer threads generate data and put it into a shared buffer, while one or more consumer threads retrieve and process the data from the buffer concurrently. So it's kind of a pattern which is used to teach the concept of synchronization. So consider this image here. So let's assume that this thing is some sort of buffer, some sort of container or placeholder where we want to put some data. But the catch here is that producer is the one which is going to put this data here, and the consumer is the one which is going to consume the data from here. So what I want to implement now is two threads. One is the producer thread which will be putting data in this particular shared container, and the other thread is the consumer thread which will be consuming data from this shared container. And at the time when the container is full, the producer will stop producer, and at the time when the consumer is empty, the consumer will stop consuming. So let's go ahead and implement the same. So to implement the producer consumer problem, here's the class that I have created, and it's called as producer consumer. And there would be a supportive class called as worker. So let's create that as well. Let's call it as worker, and the worker will have two requirements. One is to produce the element and put in the shared space. So let's call this as public void produce, and the other would be public void consume. Using this, the worker can consume from the shared space, and this worker will need certain properties. So the first one is sequence. So essentially what we are going to put in the shared space is number. So 0, 1, 2, 3, 4, 5, something like that, and it will start from 0. So we are calling the same as sequence as 0. The next thing is private final integer. Let's call this as top. So this is the maximum number of elements that can be stored in the shared area, shared container. Let's have another parameter called as bottom. So this is the least amount of elements that can be kept in the shared container. And the next thing is private final list. So this is the container itself. Here we will be placing these numbers that we are generating. So here the producer will be generating the numbers and the consumer will be consuming from. The next is that we need some sort of lock. Let's create the lock as well. Let's call this as lock and initialize this as an object. In order to initialize all these things, we will have to have a constructor. Alright, looks fine to me. Now let's go ahead and implement the produce method. So first thing is that we need to synchronize on the lock, and what I want is that produce should be able to keep on producing these numbers infinitely until a certain condition is met, and likewise, and the consumer should keep on consuming infinitely until certain condition is met. So let's start with producer. So let's call this as while true, and if container.size is the maximum one, then let's print a message. So essentially the container has become full. So container full, waiting for items to be removed, and since we are waiting, we will call dot wait, and this wait will have to throw an interrupted exception. So let's add that. and if it's not full, then let's print a message. So sequence added to the container, and let's add this to the container, and let's call notify. And in order to see the demo, we should add some sort of delay. So let's add a delay of, let's say, 500 millisecond. So what's happening here exactly? Well, this thing for sure is going to run infinitely, and that is the reason we are getting certain warnings. So may not be the most optimal way to implement this scenario, but this is fine for the demo purposes. Moving on, coming to the logic. So first thing which is checked is the container full? If the container is full, then this message is thrown and the thread goes to a waiting state. Else, and then we start adding to the container. What we do is we first print the message and then we add that sequence number to the container, and after it is added, we increment that number. So it's a post increment, so that the next number could be added to the container in the sequence. Now we are calling log.notify. So if you remember the notify discussion from a few minutes back, what we understood is that notify does not come into existence immediately. Rather, whatever is there in the synchronized block, everything will be executed, and only after that is executed, then notify will come into effect and the other waiting threads will be notified. So here what happens is that we call notify and then the call comes here. So since we are into while.true and we check that container size still not full, then we come to the else and then we go about executing this. So this happens till the time this size is not full, and then log.wait is encountered and then this thread goes to a waiting state. So this is how this thing is implemented and executed. Now let's go ahead and implement the consume method as well. Now let's implement the consume method. So for the consume as well, let's throw the interrupted exception because we will need to at the later point of time. Alright, so let's put all of this inside a synchronized block. And like we did for the case of produce, we want this to run infinitely as well. So we will put this inside a continuous while loop, and if container.size. So if the container is empty, then we don't need to consume anything. So let's print a message, container empty, waiting for items to be added, and then let's go to a waiting state. In the else section, let's start consuming. So what we say is container dot remove first, and then removed from the container. So basically we are going to remove from the list, that is the shared container, and print the message. And once this is removed, then we will call log.notify. And here as well we will have a sleep for, let's say, 500 milliseconds to show the simulation in somewhat slower manner so that it's easy to read and understand, right? So let's understand what is happening here. We are going to do this infinitely, and initially we check if the container is empty. If it's empty, print a message and go to a waiting state. If it's not empty, come to the else section, and then let's remove the element from container and print it on the console, and then we call notify. And given the fact that notify is not realized immediately, it will keep on executing whatever is there in the synchronized block, and since this entire thing is there inside this while loop, this will keep on executing till the time we are not meeting a scenario of dot wait. So this keeps on happening, and finally we encounter a situation wherein it becomes empty, the container becomes empty, wait the log.wait, and we go to the waiting state, and then this particular thread which had gone to the waiting state earlier comes into effect, and then it starts adding again. So this is how this is going to work. Now let's implement the main method. So of course we will have to move all this worker class outside this particular class. So let's keep it outside. So in the producer consumer class, let's create the main method. And in the main method, first of all, we will create a worker object which will be initialized with 5 and 0. So the shared container could contain up to 5 elements maximum, and minimum would be empty. So let's create the threads. Call this as producer. Create another thread. Let's call this as consumer, and inside the producer thread we can say worker dot produce, and of course it's going to throw interrupt exception, so let's handle it accordingly. And here we could call consume, let's handle it accordingly. And finally let's start these threads. So producer dot start, consumer dot start. So let's run this and see what we are getting. So let's run this. Alright, so here is the output. So you can see 0 added to the container, 1 added, 2 added, 3 added, 4 added, so on and so forth. Now let's stop it and analyze. So basically first 0 is added, then 1 is added, and so on and so forth. 4 is added, and once 4th is added, then the container is full, and then it's going for a state where it wants the items to be removed, and then the consumer part is activated and it's going to remove the items from the container. So 0 removed, 1 removed, and so on and so forth, and finally the container becomes empty, and then it's waiting for the items to be added. This process will keep on happening because we had implemented in such a way that it's going to happen for infinite time period. And this is one way in which we could implement the producer consumer problem. Of course, there are many other ways as well, but this is one way in which we could implement it. Till now, we have learned a couple of ways in which we can create threads in Java, such as creating the threads using extending the thread class and implementing the runnable interface. How can we create multiple threads? Let's say if we want to run 5 tasks, then we can create threads in the for loop and run these tasks. What can we do if we want to execute 500 tasks synchronously? We can for sure create 500 threads using the for loop, right? But where does it stop? What do we do if we have to run 1000 tasks, create 1000 threads in a loop? Well, something does not sound right here. Here is the problem. In Java, one thread is equal to one OS level thread. Creating a thread is an expensive operation. So creating 1000 threads in a loop is certainly not a scalable approach. What could be a more practical approach is to have a fixed number of threads, and let's create them upfront. Imagine a pool of n threads, and these threads handle the 1000 tasks among themselves. And this is exactly what the executor service helps us in achieving. In one line, we can define the executor service as a tool in Java for managing and running tasks concurrently across multiple threads. So executor service helps us in creating a bunch of threads, a pool of threads, thus the name thread pool. And the threads are not killed once they are done executing the task. Rather, they are reused to execute the another task. Thus, by making use of the executor service, we save time needed for thread creation and making things more efficient and manageable. There are 4 types of executors provided by the executor service, and these are single thread executor, fixed thread pool executor, cache thread pool executor, and scheduled executor. Now let's quickly visualize how internally the executor service looks and functions. So imagine a execution of the main thread, which is this one. This is the execution line, and the main thread calls for the executor service. And now the executor service, the way it functions is that it maintains a thread pool. There are a couple of threads that are there inside the thread pool. This depends on the type of executor we are using, but essentially you will have a couple of threads which are created in advance. Then each type of the executor service will have a blocking queue, and this is where the tasks are placed. So when we say executor.execute and the task, So what I want is that a task should be picked by either of these threads and it should be executed. But for the time being it's not getting executed, it will be sitting inside this blocking queue. So in nutshell, the executor will have two things. First is the thread pool and then there is a priority queue. And there are just two steps. The new task will keep on adding to the blocking queue and the thread which is available to execute the new task can pick the task from the blocking queue and starts its execution. And once the execution is done and the thread is available to pick another task, it will pick another task from the blocking queue. So more or less all the executors look similar to this, and this is the way in which they function. Of course, there are certain fundamental differences in which the queue will be managed and the way in which the threads will be created. Now what we will be doing is write some code making use of these executors and then understand how do they work. So let's begin. In order to demonstrate the working of the executor service, I have already created this package, that is the executor service, and now we will learn about the single thread executor. So let's create a class. Let's call this as single executor demo. We will have a class. Let's call this as task, and it's going to implement a runnable, and it will have a task ID. So let's call this as task ID. Let's have the constructor. Let's override the run method. And in the run method, we will print a message task with ID, task ID being executed by thread, and then thread dot current thread dot get name, and let's put some sleep in the thread. Let's have it for half second, and in the catch handle the interrupted exception. So we will just throw the exception for now. Let's call this as a runtime exception and pass the exception here. Here we will create the main method, and in the main method what we will do is we will create the single thread executor now. So in order to create it, we have the executors dot new single thread executor, and let's assign this to service. Now the IDE is complaining and showing some warning message. Let's see what does it say. It says that executor service used without try with resources statement. So the executor service should be closed once we are done using it. There is a way in which we could close it, and that is by calling the service.shutdown. But there is a different approach as well in which we can implement the same, and that is to use the try with resources. So let's do this and put it under the try with resources, and now we should be good to go. So let's say I want to run this task 5 times. So for int I as 0, I less than 5, I plus plus, and I can say service dot and then call the execute. So what is the runnable that I want to execute? That is my task, and pass I as the task ID. So as opposed to what we were doing earlier, that after creating the thread we used to call the dot start in order for the thread to get started with its operation. Here we don't need to do it. Rather, once we submit this to the executor service by calling .execute, it is handled by the executor service itself. Now let's run this code and see what is the output like. So let's run this. So here is the output. So basically it's going to print task ID with 0 being executed by this particular thread, and task ID with 1 being executed by this particular thread, and so on and so forth. So this is what we have implemented in the code as well, right? The idea is that there is a runnable, and what it does is it's simply going to print the task ID along with the thread by which it is getting executed. So if we had not used the executor service, what we would have done is we could have created 5 threads, and using those 5 threads I could have assigned the runnable for each of the thread and then should have called the dot start on that. But here we are able to achieve the same kind of result using the executor service and this implementation in particular, which is new single thread executor. So now the implementation looks much more cleaner and we don't have to deal with the creation and destruction of the threads. Now everything is being handled by the executor service itself. Let's learn how the single thread executor works under the hood. So we have the main thread, and this way we can create in tasks and submit or execute those tasks one by one. So here we have the thread pool, and in the thread pool there is a single thread. There is a task queue which is containing task 0, task 1, task 2 up to task n, and what this single thread executor will do is it will pick the task from the task pool or the task queue and then execute it. So fetch task and execute. So in the case of single thread executor, the size of the thread pool is just 1. So we have just one thread which is going to fetch the tasks from the task queue and run this. And if it so happens that due to some exception the thread is killed, the executor will make sure to recreate the thread and the execution of the tasks won't be stopped. By using this kind of thread pool, we can ensure that the task 0 is always ran before task 1 and task 1 is always ran before task 2. Since we have just one thread here, it's guaranteed that the tasks would be ran sequentially. Now we will learn about fixed thread pool. So let's create the class. Let's call this as fixed thread pool demo. Let's maximize this one. And as we had done earlier, we will be creating a runnable, which will be the task which needs to be executed by the executor service. So let's do that. Let's have a class called as work. It's going to implement a runnable, and we can start by overriding the run method. So public void run, and it will have certain parameters. So the first field is work ID, and then it will have a constructor which is going to initialize this work ID. And in the run method, what we will do is we will print a similar kind of message, the task ID. Let's provide the work ID here, being executed by thread dot current thread dot get name. Let's put some sleep timer here. So again, let's go with half a second, and in the catch, let's handle the interrupted exception. Let's throw a runtime exception and pass the exception. And now let's go to the main method, and very similar to what we did for the single thread executor, we will also be creating the executor using the try with resources. So try executor service, let's call this as service, and executors dot new fixed thread pool. Let's say that I want to have a thread pool of size 2, and I want to execute this task 7 times, or what you could say is I want to run 7 tasks. So let's make that. So int I as 0, I less than 7, I++, and let's call service dot execute new work, pass the ID. So let's print this and see how is the outcome like. So let's run this. So here is the output. So task ID 1 is being executed by thread 2, task ID 0 is being executed by thread 1, task ID 2 is being executed by thread 2, and so on and so forth. So one important thing to note here is that since we had two threads created, these two threads are there in the thread pool and they are taking turns in order to execute my task. So first thread 2 is being used to execute the task, then we have thread 1, then I have thread 2, then we have thread 1, thread 2, thread 1, thread 2, and so on and so forth. Please note that this may not be alternating in the stricted terms. This is just an instance wherein we got this kind of pattern, but this does not mean that in all the cases it will be one by one. It could so happen that thread 2 could execute certain tasks in one sequence, and then after that thread 1 could be invoked, and then thread 1 could be assigned with certain tasks for execution. So this is what we have achieved by making use of the fixed thread pool. So to sum it up, we have created a new fixed thread pool and there are two threads, and when I want to execute 7 tasks, then those 7 tasks are picked one by one by either of the available two threads and they are executed. Now let's have a quick look around how exactly does the fixed thread pool work under the hood. So what you see here is a visual representation of the fixed thread pool executor. And here in the case of fixed thread pool, there is a fixed number of threads. As the name suggests, that there will be certain number of threads which is pre-created. And this executor also has a task queue where all the tasks will be placed. So consider this as a task queue of some sort. The threads in the fixed thread pool pick the task from the task queue and execute them. So when the thread is done with the execution of a task, it goes ahead and picks another task, and this keeps on happening until all the tasks are completed. So the basic idea remains the same, that there is a thread pool and the threads are fixed in the count, and once you have tasks flowing in the task queue, these threads will start taking out the task from the task queue, start to work on those, and once all the tasks are done, and this keeps on happening till the time the task queue has certain tasks in it. So overall, this thread pool executor is fetching the task and executing it over and over again. Now let's learn about the cached thread pool executor. In order to do so, we will write a code to demonstrate its functionality, and let's name the class as cached thread pool demo. We will have a task, so create a class for the same. Let's call this as task1. It will implement the runnable interface. Let's override the run method, and this class will have some sort of task ID. Let's call this as task ID. Initialize the same inside the constructor, and it can give some message, something like task, then task ID plus being executed by thread dot current thread dot get name. Then we will put this thread to sleep for, let's say, 500 milliseconds and surround this with try catch. Now let's write the main method, and we have executor service. Let's call this as service, and what we want is new cached thread pool. Let's keep it inside the try with resources, and one key thing to observe here is that there is no value that we are going to pass inside the new cached thread pool, unlike the fixed thread pool where we were passing the number of threads that we want to create a front. Why is it so? We will see in the next section. For now, let's run this thing probably for maybe 1000 tasks. So I less than 1000, I plus plus, and service dot call execute new task 1 and give it a task ID of I. So let's execute this and see its output. Alright, so here is our output. You see, all the tasks are being executed by the threads that are getting created. So task 27 is being executed by the thread 28, task 41 is by thread 42, task 4 is by 5, and then task 1 by 2. So that's it for the code demonstration. Now let's understand how does it work internally. Now let's visualize and learn the internal workings of cached thread pool executor. In the case of cached thread pool, we don't have a fixed number of threads. So you see, in the code implementation, we did not provide any number to the method which was creating the new cached thread pool. The task queue here does not hold a number of tasks which we submit. The queue here is of a special type and it's called as a synchronous queue. The synchronous queue has space only for a single task. So every time you submit a new task, the cached thread pool holds the task in the synchronous queue and it searches for the threads which has been already created and they are not working actively on any task. If no such thread is available, the executor will create a new thread and add it to the thread pool, and this newly created thread starts to execute the task which has been submitted. Let's imagine a scenario where 10 threads are executing 10 tasks at a given point of time, and then 11th task comes in, and since we don't have a thread 11 to cater to this task, the thread pool will create the 11th thread to execute this new task. So in theory, the cached thread pool is capable of creating thousands and thousands of threads. You may wonder, where does this stop? If threads are getting created at such a rapid pace, so what is the upper limit? Well, there is a guardrail to keep the thread count in check. After some time, the threads are done executing the tasks and they are available to pick another task. And if they don't have any other task, they are killed, and this time of idleness is 60 seconds. So what I mean is, let's say there is a thread and it has not received any task to work upon, it will be terminated. So cached thread pool is pretty much auto-scaling in nature on the basis of task load it has. When there are new tasks to be executed, threads are added, and when there are less number of tasks to be executed, a few among the created threads could handle the task, so the other threads, the idle ones, are retired and killed. So that's how the cached thread pool executor works behind the scenes. So the basic takeaway from here is that the queue will contain only one task at a given point of time, that is your synchronous queue, and the maximum time for which a thread could be there in the thread pool without any work is 60 seconds. So now let's move ahead and learn about the final type of executor, which is the scheduled executor. Now let's write the code for demonstrating the scheduled executor service. Let's create this class. Let's call this as scheduled executor demo. We will create a task. Let's call this as probe task. It will implement the runnable interface. Let's override the run method. And run method is going to print a message. Let's say probing endpoint for updates. Let's create the main method. So we have scheduled executor service. Let's call this as service. And from the executors, let's call the new scheduled thread pool. New scheduled thread pool. Let's have the number of threads as 1. And the scheduled executor service does offer a couple of methods in which we could schedule the threads to be executed. We will go ahead with the implementation, which is scheduled at fixed rate. So the idea is that this particular thread will be executed at a fixed rate after certain point of time. So the way to write this is service dot schedule at fixed rate. So we have the actual runnable, then the initial delay followed by the period and then the time unit. So runnable is the runnable, initial delay is after how much time this execution will start. So let's say you could pause for 2 seconds, and then after 2 seconds, every 3 seconds this thread could be executed. So let's write it. So the runnable here is the probe task, and let's say the first delay that I want is of 1000 milliseconds, and I want this to run every 2000 milliseconds, and the time unit is going to be milliseconds. Now let's execute this and see how is the output like. So we are seeing that this thing is getting printed, probing in point for updates, and it will keep on printing this every 2 seconds, and it will keep on printing this probing in point for updates till the time we shut down the executor service. So how can we do that? Let's stop this and write some code for the same. So the way to do this is we can call the await termination method on the service handle, this object, and supply certain time. So it will wait for the executor to be terminated in that time range, and if it's not terminated in that time range, it will call the shutdown method of the executor service, which is going to gracefully terminate the executor service. So let's write the code for same. So we will put this inside a try block because await termination is going to throw an interrupted exception. Let's have the interrupted exception as well, and in the try block we can check service dot await termination. Let's give it a time of 5000 milliseconds, and then time unit is milliseconds. So if the time is more than 5000 milliseconds, we can call the shutdown method. So let's say shutdown now, else if it goes to the interrupted block, there as well we could call shutdown now. Let's increment this time to maybe 10 seconds, and now let's run the code and see its output. So you see, the delay that we had was of 2 seconds, that every 2 seconds this should be printed, and after printing it for 5 times, that is like 10 seconds, it got terminated on its own. So that is how we could terminate the scheduled executor. So of course this is a very crude and basic way of writing things. In real world, probably we could have this termination logic on certain condition, and when that condition is getting fulfilled, we can call the shutdown method and close the executor service. So as I told earlier that this is one of the methods which is provided by the scheduled executor service, I will suggest you that as part of exercise, you could try to go inside the scheduled executor service and explore the entire interface, as in what all different scheduling options are there. For example, we have a schedule, then we have this schedule method signature, then we have something called as schedule at fixed rate that we implemented, then we have something which is called as schedule with fixed delay. So I think it will be a good exercise for you to go inside this class and learn about these methods. And the other thing is that we have called shutdown now. So what it means is that this is a strict guideline to the executor service that whatever you are doing, stop doing that and shut down the operations of the executor service. There is another method, however, which is called as shutdown. So shutdown is somewhat more graceful in nature, and the way it works is that it initiates an orderly shutdown in which previously submitted tasks are executed. So whatever is there inside your task queue, those will be executed, and only after that the executor service will be shut down. But once you call shutdown, then the new tasks won't be allowed to come inside the task queue. But in the case of shutdown now, all the actively executing tasks are also halted and stopped. So this is the basic difference. Now we will have a quick look to understand and visualize the internal workings of the scheduled executor service. So as we saw earlier that this thread pool is for the kind of tasks which we want to schedule in some manner. And the way this works is all the tasks are submitted in a task queue, but this queue is a delay queue. In the delay queue, tasks are not kept in sequential manner. We can understand this to be some sort of priority queue, where the priority is the time of execution. So if there are two tasks, for example task 0 is supposed to be run after 10 seconds from the current time, and task 1 is supposed to be run after 15 seconds of the current time, then in that case task 0 should come earlier as compared to the task 1 in the task queue. Likewise, if task 1 is supposed to be executed first before task 2, then it should be coming earlier in the task queue. So everything else remains the same other than the queue, which is a delay queue in the case of scheduled thread pool executor. How do we find the ideal pool size for the thread pool? Well, like most of the answers in computer science, the answer to this question as well is that it depends. However, it's worth discussing what it depends on. So let's get started. Imagine that you have a CPU intensive task which needs to be executed. Please note that in Java, one thread is one OS level thread. So if your CPU has 4 cores, then at maximum you could execute 4 tasks in parallel at once. So on a hardware which can only support up to 4 cores, creating hundreds of threads won't help if they are CPU intensive. In fact, it leads to a performance degradation. Let's focus more on why there is a performance degradation. When you have 100 threads to run your CPU intensive task, then all such threads will try their best to get their pie of the time allocation with the CPU. When this time slicing happens beyond a certain threshold, the expense of content switching overpowers the benefit we get from making use of the multithreading. So lots of threads contesting for CPU time is counterproductive, and in such a scenario, having too many threads is not a good idea. What we can do rather is have the same number of threads as the number of cores in your CPU. But please note that having created the same number of threads as the number of cores in your CPU does not ensure that all the cores will be running your threads only. Some of the cores will be utilized by other tasks and OS level processes as well. So how can we do this? Let's say a quick code example. In the executor service package, let's create this class. Let's call this as CPU intensive task. So let's create a task class and maybe let's call this as CPU task. It implements a runnable. Let's override the run method. And all it does is it prints some message like some CPU intensive task being done by the and thread dot current thread dot get name. Let's write the main method. In the main method, first we will try to get the number of the cores, and we can do so by making use of the runtime. So runtime dot get runtime dot available processors. Now let's create the executor service. Call this as service executors dot new fixed thread pool, and it could accept the number of cores as the number of threads it wants to create. Let's print a message for debug purposes. So created thread pool with cores. Next, let's execute our task. So let's say I want to execute 20 tasks, and service.execute a new CPU task. Let's run this and see the output. Here is the output. So created thread pool with 14 cores. So my machine has 14 cores, and what it does is it says like some CPU intensive task being done by thread 1, thread 2, thread 10, thread 14, thread 14. So what we say is it has created 14 threads, which is the number of cores, and then those 14 threads are being used to execute the 20 tasks that we want to execute. So now let's learn about the other type of task. So there is another type of task which is IO intensive. Such IO intensive tasks are inherently fire and forget in nature. This is because IO operations such as reading from files or making network calls often involve waiting for external resources to respond. During this waiting period, the CPU is idle, and having more threads allows other tasks to execute while one thread is waiting for the IO operation to complete. However, here as well, it's not recommended to go crazy with the countless number of threads. Rather, the more sane approach is to experiment with thread pool sizes. This will help you to find the optimal balance between concurrency and resource utilization. So to summarize, there is no single answer for the question of what's the ideal thread pool size. What you could do instead is analyze your task patterns and based on their type, utilize a combination of the above mentioned approaches. Till now, we have seen how can we execute threads using the executor service. But something seems not complete. In all the examples that we have seen so far, we are not returning anything. What if we want to return something from the thread execution? How can we do that? Let's learn about the same. So here I have created a class. This is called as Callable Demo, and we have a class for the task which is implementing the Runnable interface. And inside the run method that we have overridden, I'm trying to return something. Well, of course it's giving some compilation error because at the moment there is no way in which I could return some value from this method. Why so? Let's go to the Runnable interface, and what we see here is that the Runnable interface has just one method which is run, and it's returning a void. That means we cannot return anything. So what is the solution? So if we want to return anything from a thread, the way to do this is implement the Callable interface. So Callable is another interface provided in Java, and the way it works is that you implement this interface and it's a generic based class, so you'll have to pass the generics of what exactly you want to return. So let's say that I want to return an integer, so I'll pass the same. And now let's get rid of this one and see what are my implementation options. So like we had run in the case of Runnable, in the case of Callable we have call, and here whatever you provide in the generics, the same thing is applied here, that is the integer. And let's say I want to return 12, so now this 12 should be returned whenever I'm going to run this thread. But now this part of the code starts to give some error. So what is the problem? Well, the problem is that executor service provides two ways in which we can execute or submit threads to the executor service. One is the execute, other is the submit. So let's replace this with the submit, and now this should work fine. So what submit expects us is to pass either a runnable or a callable. So even if you want to pass a runnable, that is fine with submit, and for callable anyway you have to use the submit method itself, because you cannot submit a callable by using the execute method. So now that we have called the .submit on the executor service, what does it return? Should it return an integer? Let's find it out. So what we see here is that this thing is going to return a future. So what is a future? Future is again a class which is generic based, and in this case, since we were returning an integer, it's going to supply this integer value over here, and using the result we can do a couple of things, and one of those things is calling the .get method on this result. So let's print it out, and it's giving some error. Reason is that it is expecting us to either add a catch clause or maybe surround with try catch. So for now maybe I'll just add the exception method to the signature. So now let's run this code and find out what is the outcome. So yes, indeed it's going to return the value, that is 12, and this is how we are supposed to make use of callable if we want to return some value from a thread execution. But there are a few things we should be mindful of while using the callable interface and calling the .get method on the future class. Let's learn about the same. So what we have here is the main thread. So assume that this line is the main thread execution, and then at some point of time you created a callable and then you did a submission of that callable. So once that callable is submitted to the thread pool, you will immediately get a future of the type of the generics for the callable that you have implemented. And using the future object, sometime down the execution, you could call future.get. So what happens is future is a placeholder. and it's empty till the time the processing is not completed by your thread. And that time could be anything depending on the execution that you have in your code, right? So let's say at this point of time you called future.get and the future did not have the final calculated value. So what happens? Please note that future is a blocking operation. What it means is that if you call future and if there is no value inside the future, then your entire main thread execution will be blocked. So whatever was being executed by the main thread, that will be entirely blocked. Let's say at some point of time the future got the value, so you will be able to get the value from here and then the execution will resume or start. So this is one thing that you should always keep in mind while making use of the future.get call. So now let's demonstrate the same thing. Let's give another print statement. Let's call this as main thread execution completed. Let's run this. So we can see that the result is pretty much instantaneous. So we are getting a result as soon as possible. Now let's put some sleep in this thread. So let's call thread.sleep. Maybe let's have a sleep timer of 5 seconds. And with this, let's try to execute this one more time. So we are waiting. There is no result as of now. So just after 5 seconds, once the execution got completed, then we see this line that main thread execution completed. So basically what we did was we introduced some sort of latency in the call method, and when we called result.get, since the future did not have the result populated for this, so the main thread was blocked, and as soon as this future got its value, the value was printed and the execution continued. So is there any workaround for this behavior? So result.get has an overloaded method with this signature where you could pass in the timeout. So what this will do is it will wait for a certain time before giving a timeout exception, and in that time duration, if the future does not have the value, it will throw an exception and move ahead in the execution. Otherwise, if you get the value in that timeout, it will work as expected. So let's try the same. Here it's expected that this call method will be taking 5 seconds to run. So let's try to put a timeout of 1 second. And let's pass the time unit of second. This thing throws an exception. Let's handle that. Now let's run it one more time. After 1 second, it could not find the result, and then it threw an exception, that is the timeout exception, and it ended the execution. So if you don't want to end the execution this abruptly and probably continue with your execution, you could handle this exception in some other manner so that the execution of your main thread continues. Now let's increase this value to 6 seconds and find out the result. So now, since we have provided a timeout of 6 seconds and this thread needs 5 seconds to complete, the execution got completed, and then we had this message printed on the console, that is main thread execution completed. So this is good, but is there any other way in which we could handle the futures? So there are 3 important methods that we should know. So the first one is future.cancel, and it expects us to pass a true or false. So let's say if I pass true, then let's say what exactly does it mean. So this value is may interrupt if running. So if you pass true, then let's say if the thread is running, then in that case it may get interrupted. If you pass false, then it will not be interrupted. So this is about the .cancel method. The next thing is future.isCancelled, and this returns a boolean. So using this, you can check in your code that the given future, is it cancelled or not, and based on that you could implement certain functionality in your class. There is another important method which is called as isDone. So it's result.isDone, and this again results into a boolean value, and what it signifies is that whatever thread was being executed has that completed. Please note that this will return true for both the cases where the thread is going to run successfully and return some value, and in those cases as well wherein the thread is getting interrupted or maybe exiting out due to certain error or exceptions. This is the way in which we can make use of the callable interface, and based on your use case, you can use either Runnable or Callable to implement threads in Java. Java has a rich set of collection classes. However, most of them are not thread safe. We need to take precaution to ensure that the collections are behaving as intended when used in a multi-threaded context. There are two ways to do so. The first approach is to use the collections.synchronized method, and the second approach is that we can use concurrent collections, which are essentially concurrent versions of the collections. In this video, we will learn about the first approach. In order to demonstrate the uses of collections.synchronized method, I have created this class called as synchronized collection. So let's start by creating a array list. Let's call this as list. And I will be creating two threads. The first one is called as 1. What this will do is it will add some value to the list 1000 times. So list.add I, and let's close this one. I will be creating another thread, and it will also add some value to the same list 1000 times. List.add I. So let's move these things to the main method, otherwise this will not work. Let's create a main method. Let's place the things here. And now 1.start, 2.start. And in order to ensure that these threads are getting completed, let's call the .join on these two methods. Second is 2.join. And now let's print the size of the list after the operation has been completed. Now let's run this program and see what is the output. So you see the output is 1446. However, we are adding value to the list 1000 times, and this is being done by two threads. So what we should have expected is that the value would be 2000. But here there is a mismatch. Let's run it one more time. And this time we are getting a totally different value. So the point here being that it's leading to some sort of inconsistency when this is being used by different threads. So how can we solve this? So one approach is to make this thing as synchronized. So as discussed earlier in the video, that there are two approaches to make use of the concurrent collections in Java. One is by using the collections.synchronized method, and the other is to use the concurrent collection itself. So here we will be learning about the synchronized method. So let's do that. And the way to do this is, let's comment it out. Let's create a new one. So list integer list, and we can call collections dot synchronized. So you see there are lots of options: synchronized list, synchronized collection, map, set, navigable map, so on and so forth. But in this case we have to synchronize the list, so we will be calling synchronized list, and we will pass an array list. So this is the way in which we can create a synchronized list using the collections.synchronized method. And based on your need, you could also invoke other things like synchronized map and synchronized set and all those things. So let's run this thing one more time and see the output. So we are getting the value as 2000. So basically list.size is 2000 now. Let's run it one more time. And now we should be getting the same value through and through. So this means now there is no inconsistency in the list, even though we are using it across multiple threads. So the list is a synchronized list now. So this is the way in which we can use collections.synchronized to help us with creating a concurrent collection. However, there are certain downsides of using the collections.synchronized approach. Let's learn about those one by one. So the first one is coarse-grained locking. What it means is that it uses a single lock to synchronize all the operations on the collection. This means that only one thread can access the collection at a given time, even if multiple threads are performing unrelated operations. This can lead to contention and reduced concurrency, especially if there are frequent read and write operations on the collection from different threads. The second is the limited functionality. And what do we mean by the limited functionality? Well, the synchronized wrapper returned by the collections.synchronized list does not expose any additional methods for fine-grained locking or custom synchronization strategies. This limits your ability to optimize synchronization based on specific uses or patterns of your application. So when we discuss about the concurrent collections, we'll try to cover how exactly those collections provide certain other custom synchronization strategies as well. So the third downside is that there are no fail-fast iterators. So collections returned by collections.synchronized list do not support fail-fast iterators. The fail-fast iterators throw a concurrent modification exception if the collection is structurally modified when an iterator is iterating over it. Without fail-fast iterators, it's possible for concurrent modifications to the collection to go unnoticed, and this can lead to certain unexpected behaviors. The fourth downside is performance overhead. So synchronization introduces overhead due to lock acquisition and release. This overhead can degrade performance, especially in the high throughput or latency sensitive applications. So if at all you don't need these four things, then probably you could consider making use of the collections.synchronize method in your use case. But let's say if you require some of these functionalities or these features, it's better to go with the concurrent collections which are provided by the Java. So now let's start learning about those concurrent collections. Let's learn about the countdown latch. Countdown latch is a synchronization utility that allows one or more threads to wait until a set of operations which is being performed in another threads completes. It is part of the Java util concurrent package and can be used for controlling the flow of execution in the concurrent programs. The key concept of countdown latch is that it maintains a count that it starts from a specific number and decreases each time the countdown method is called. Threads that need to wait for the countdown to reach 0 can call the await method, which will block until the count becomes 0. So when to use countdown latch? Let's understand the scenario in which we can use countdown latch with a very simple and easy to understand example. Imagine you are a tech lead who is leading a complex project. Being the expert which you are, you divide the complex task to some smaller and simple to implement tasks. After splitting the task, you distribute them with your team and they start working on their respective tasks. However, now you cannot proceed further on this project until they all complete their task. In scenario like this, you can use a countdown latch. Countdown latch is like a checkpoint for each team member's progress. You set up the latch with the total number of tasks or team members. Each member, upon completing their task, calls the countdown method of the latch. It indicates that they are done. As the organizer, you wait for all the tasks to be completed by calling the await method. This method halts your progress until the count reaches to 0, meaning all tasks are done. Once all the tasks are completed, the latch opens up and you can proceed with the next phase of the project. So, countdown latch helps in coordinating multiple threads or tasks to synchronize their work. It ensures that they all reach a certain point before proceeding further. So let's have a quick code demonstration on how we can use the countdown latch for developing certain use case. We are in the concurrent collection package and I will create a class. Let's call this as restaurant, and I will implement a task. Let's call that as chef and let it implement the runnable. So before we move ahead with the implementation, let's discuss a bit about what we are planning to implement. So what we are planning to build here is a simulation where a group of chefs need to prepare different dishes in a restaurant kitchen. Each chef is responsible for preparing a specific type of dish. And the kitchen manager wants to start serving customers only when all the dishes are ready. So here is how we can use the countdown latch to coordinate all the chefs. So let's proceed with the implementation of the chef class. So first thing is, let's override the run method. So with that in place, let's have a few properties of the class. So first is a string, which is name. The second is again a string, which is a dish, and third field is going to be the countdown latch itself. Let's initialize all these fields in a constructor. So now that we have initialized all the fields in the constructor, here is what we are going to have in the run method. So we try to simulate the preparation of the dish, and for that let's have a try block and then a catch block. It's going to throw an interrupted exception. Let's call this as E, and for now just throw a runtime exception. And for the try block, what we will be doing is, first we print a message like name is preparing and then the dish. Next, let's have a sleep time of 200 milliseconds, and the idea is that this is the simulation for the cooking time. So essentially your chef is going to cook for 2 seconds. Quite a fast chef, right? He is cooking in just 2 seconds. Anyway, so let's have another print statement, and what this will be printing is name plus has finished preparing and the dish. So till now what we have tried to mimic is that the chef is going to prepare some food, and once they are done preparing the food, this message will be printed, and what it means is that the task has been completed. So what we will do is we will call latch.countdown. So that should be it for this class, that is the chef class. Now let's implement the main method in the restaurant class. So let's have an integer value. Let's call this as number of chefs. Let's say we have 3 chefs, and what we will do now is we will create the threads for the 3 chefs and then we will start those threads. The way we can do this is new thread, and it could accept a new chef. Let's name this as chef A. Let's assume the chef is preparing pizza, and then we pass the latch. So we have not created the latch yet, we will create in some time, and then let's call the dot start method on this one. So let's create the latch. So let's have the countdown latch. Let's call this as latch, and new countdown latch number of chefs. Let's create a same kind of thread for the another chef as well. So new chef, let's call this guy as chef B, and let's assume that this guy is preparing pasta. So let's call latch and let's call start. Let's duplicate this, and let's say this guy is preparing maybe salad, and this guy is chef C. So when we have created the threads and called the start on these threads will start running at some point of time, and then we should make use of the latch somehow in order to ensure that this entire thread of execution, that is this one, is blocked till the time all these 3 threads are completed, right? And the way to do this using the latch is call the await method. What does await method do? It will ensure that the thread is waiting for all the dishes to be completed. Eventually 3 threads are there, all those 3 threads are done with their execution, and await will expect us to handle some exception, and either we could add into the method signature or surround with try catch. For now let's add to the method signature, that is an interrupted exception, and once this is done, then we can print a message that all the dishes are ready. Let's start serving customers. So this is what we have implemented. Let's try to run this and see its output. So when we call dot start, the message is printed that Chef C is preparing salad, chef A is preparing pizza, chef B is preparing this pasta. And after 2 seconds, all these 3 chefs are done. And what they do is they print chef C has finished, chef A has finished, chef B has finished. And when these guys are finishing with their preparation, they will be eventually calling the last dot countdown. And since we have defined a value of 3, that is the number of chefs, which was 3 here, so this countdown latch has a value 3 to begin with. And the way it works is that last dot await will hold true, or rather it will hold the execution of the thread on which this has been called till the time it does not reach 0. And by the time the third chef is done, that is chef B has finished preparing the pasta, then in that case that thread will be calling the latch dot countdown, and once that countdown is invoked, it means that the countdown becomes, the counter rather becomes 0, and at that point of time this will be unlatched, and then the thread will be unblocked for the further processing, which is system.out, and this message will be printed. So this is what the countdown latch does, and this is the way in which we can make use of this for our use cases. Now you may have a doubt. You may think that in the beginning of the video we learned about the join method. So is it not very functionally similar to the join? So let's understand that. So from the purpose perspective, countdown latch is designed to allow one or more threads to wait until a set of operations in other threads complete. It is typically used for coordination among the multiple threads. Join, on the other hand, is used to wait for a thread to complete its execution before proceeding with the rest of the code. And it's specifically used for thread synchronization within a single threaded context. So how exactly are these two things different from the user's perspective? So the countdown latch is useful when you have multiple threads performing independent tasks and you want to coordinate them before moving forward. And join is useful when you have a main thread that spawns worker threads and needs to wait for them to finish before continuing its execution. So I hope these points should have drawn a clear picture of the differences between the countdown latch and join method. However, you might have one more doubt left. You may think if there are 3 threads and there is a countdown latch for them, so either use the countdown latch or call join methods 3 times, which is on all the 3 threads. Is it not the same, right? So why take a pain of learning a new concept altogether? Think of this scenario where you have a dynamic number of threads. So what do? How many times and in what manner are you going to call join method on those threads? In situations like this, countdown latch shines as compared to the uses of join method. Overall, countdown latch is a much cleaner and elegant approach, especially if you are coordinating among multiple thread operations. So the final thing about the countdown latch is, can we reset the count? Well, countdown latch is supposed to be used as a one-shot solution. So you cannot reset the count. If you need a solution which resets the count, you are looking for something called as a cyclic barrier. And with this, let's learn about the cyclic barrier next. Now let's learn about a very important concurrent collection in Java, which is blocking queue. Since it's quite commonly used, we will try to learn it in somewhat more detailed manner. Imagine a blocking queue to be like a conveyor belt in a factory where items are placed and taken off. In Java, a blocking queue is a data structure which allows multiple threads to safely put items onto the queue and take items off the queue, and this is done in concurrent manner. There are 2 aspects of blocking queue. So the first part is the blocking aspect. The term blocking means that if a thread tries to take an item from a queue which is empty, it will be paused or blocked until an item becomes available. Similarly, if a thread tries to add an item to a full queue, it will be blocked until the space becomes available. The second aspect is the uses of the queue. So the blocking queue follows the first in first out principle, meaning the item that was added first will be the first one to be taken out. Now let's talk about the blocking queue interface. In Java, the blocking queue interface is the parent interface to a few other interfaces and the concrete implementational classes. So this is the parent interface, which is the blocking queue, and the two such interfaces which extend this blocking queue are blocking DQ and transfer queue. So this is also sometimes called as blocking deck or DQ. So whatever you wish to call, you could call it. Now coming to the blocking deck. So blocking deck is a double-ended queue that blocks threads when it reaches its capacity or becomes empty, thereby facilitating flow control between producers and consumers. It provides methods to access the queue from both the ends in a thread-safe manner. Due to its double-ended nature, the performance characteristics of blocking deck may differ from those of blocking queue, especially in the scenarios where there is a contention for access to both ends of the deck by multiple threads simultaneously. Key takeaway from the implementational perspective here is that it provides access from both the ends in a concurrent manner. Regarding the transfer queue, it's a specialized queue where producers can block until a consumer directly receives an item. It extends the functionality of blocking queue by providing a method called as transfer. What this method does is, it allows one thread to transfer an item directly to another waiting thread, potentially avoiding the need for blocking. If there are no waiting threads, transfer behaves like put and blocks until there is a space available for the item. Transfer queue ensures a strong handoff coordination. What does this mean? Let's understand this with an example. Imagine a factory where one worker produces items and another worker packages them for shipping. The producer worker can directly transfer the produced item to the packaging worker without waiting if the packaging worker is ready to receive it. If the packaging worker is busy, the producer worker waits or blocks until the packaging worker becomes available to receive the item. This direct mechanism can improve the efficiency in certain scenarios compared to a traditional blocking queue. So now let's learn about the major implementations of the blocking queue. The first one on the list is array blocking queue. It implements a bounded blocking queue and it is backed by an array data structure. The next one is the linked blocking queue. So this one implements a bounded or unbounded blocking queue backed by a linked list. The priority blocking queue implements a blocking queue that orders elements based on their natural ordering or according to a specified comparator. Then we have delay queue. What it does is, it implements a blocking queue of delayed elements, where an element can be only taken out when its delay has expired. It is particularly useful for scheduling tasks to be executed after a certain delay or a specific time. The final one is the synchronous queue. This implements a zero capacity blocking queue where each insert operation must wait for a corresponding remove operation by another thread and vice versa. So based on your requirement and uses, you could use either of these implementations. But for most practical purposes, the uses of array blocking queue, a linked blocking queue, or a priority queue should be good enough. Now let's have a look on the blocking queue operations. So these are the certain operations which are supported by the blocking queue. Put method adds the specified element E to the queue if the space is available. If the queue is full, the operation blocks until the space becomes available. Next is the take method. It retrieves and removes the head of the queue. If the queue is empty, the operation blocks until an element becomes available. The third one on the list is the offer method. What this does is, it adds the specified element to the queue if the space is available. It returns true if the element was successfully added or false if the queue is full, as opposed to the put method which blocks until the space is available. Poll method retrieves elements from the head of the queue. It returns null if the queue is empty. It does not block the queue if the queue is empty, as opposed to the take operation which blocks the queue until an element is available. The peek method retrieves but does not remove the head of the queue. It returns null if the queue is empty. Some of the above methods also provide overloaded signatures which allow you to pass timeout values as well. So I suggest that you explore the blocking queue interface. There you will find all the variations of the major methods which we have described here. So all the implementations of the blocking deck interface have functionally similar methods which provide these operations on both the ends. As an exercise, you could try exploring the interface and the implementations to understand them better. So now let's have a code demonstration which will showcase the uses of the blocking queue interface. In order to demonstrate the uses of the blocking queue interface, I'll be creating this class inside the concurrent collection package. Let's call this as blocking queue demo. Here is what I'm planning to implement. It will be of some capacity and there would be a couple of threads. One thread would be a producer thread. Then we can have a couple of more threads. For example, let's say 2 threads as the consumer threads. And once we start the threads, then the producer thread should be able to produce or write data to the queue, and consumer threads should be able to consume from the queue. So let's implement this. So let's start by having the queue capacity. Let's call this as queue. Next we can have the blocking queue itself. So let's declare that, and we want to put an integer value in the blocking queue. Let's call this as a task queue, and we are going to make use of the implementation of array blocking queue. Let's pass the capacity, that is the queue capacity, and let's start by implementing the main method. First on the list would be the producer thread. Here in the producer thread, what we will be doing is we will be iterating for a certain amount of time and then putting that number to the task queue. So let's implement that. So we have a try block. Let's have a catch block as well. We will have an interrupted exception. So let's put this for now. And now coming to the try block, we will have a loop which is running from 0 to 20, 0 to 19 rather, or maybe let's change the numbers from 1 to 20, and all it does is it puts this number to the task queue. So let's call put, and the value would be I. Let's print a message, task produced I, and let's have a sleep timer for let's say 100 milliseconds. So this is essentially the task generation time that we are having here. And now that we have written the producer thread, let's write the consumer thread as well. So let's have the first consumer thread. Let's call this as consumer1, and let's rename this to producer. So what this consumer thread does is it consumes from the task queue infinitely. So let's implement that. So let's start by having a try block. Let's have a catch block. Let's have an interrupted exception, and let's throw this one as a runtime exception. So while true, what we are going to do is we can retrieve the task which we have in the task queue dot tick, and then we will call a method. Let's call this as process task. So let's pass the task and the consumer ID. So let's now implement the process method before implementing the second consumer. So private static void process task, then we have the int task, then we have the consumer name, and let it throw the interrupted exception because I wish to provide some sort of sleep in this particular method. So first we start by printing a message, that task being processed by consumer name, and then print the task. Then we will try to sleep this for 1000 milliseconds. So the idea is that in real world scenario as well, when you will be processing a task, that will involve certain time, right? So here, since we have a pretty much bare bones implementation, what we are going to do is we are going to provide some sort of sleep, and that will mimic the processing time, which is 1000 milliseconds in this case. And now once we have done the processing, we can print the message, the task consumed by consumer name, and this is the task. And Now we will be implementing the second consumer thread as well. So let's call this as consumer 2, and we will have a similar kind of implementation here as well. So let's copy this one really quick, and what we are going to do is everything remains the same. So this is going to run infinitely. It's going to extract out the task from the task queue. Process task remains the same. It's just that we change the name here. So now let's call this as consumer 2, and everything else remains the same. So now let's start the threads. So producer.start, consumer1.start, consumer2.start. So I think this should be it for the implementation side of things. Let's run this code and see how is the output like. So as you can see, that task being produced is being printed by the producer method, and then task being processed by consumer 1, and task consumed by consumer 1. So we had introduced some sort of sleep, right? So during that time another thread takes over, that is the producer thread, and it's going to produce. So basically task being produced, so task ID with 2 is produced and kept in the queue. Then this task is being consumed by consumer 2 as soon as the task is available in the processing queue, right? So this is the way in which the producer is creating tasks and pushing to the queue, and the consumer on the other hand, which we have a pair, consumer 1 and 2, they are pulling the queue and they are taking out from the queue and working on that and consuming the tasks in the task queue. So you could try to implement it yourself. So using the block queue, we have implemented a simulation wherein we are writing to a thread safe concurrent data structure, which is the blocking queue, and we are able to operate on the data structure using multiple threads, that is the producer thread and 2 consumer threads. So you could go through the code one more time and try to get a hang of it if it's not very clear. So as an exercise, you could go ahead and explore these classes and try to come with certain use cases and implement those use cases using these classes. So this will really help you with your understanding of the uses of the blocking queue in the Java. Now let's learn about the concurrent map in Java. So concurrent map is an interface in Java which represents a map that can be safely accessed and modified concurrently by multiple threads. It extends the map interface and provides additional atomic operations to support concurrent access without the need for explicit synchronization. Concurrent map is needed in Java to handle the situations wherein multiple threads need to access and modify a map concurrently. Concurrent map has a couple of implementations such as concurrent hash map, concurrent escape list map, concurrent linked hash map, concurrent navigable map, etc. Out of these, concurrent hash map is probably the most widely used one, and this should be sufficient for most of your practical use cases. So now let's have a quick code demonstration, and we will implement a simple feature using concurrent hash map which showcases how this concurrent collection can be used in a multi-threaded context. So here is a brief idea behind what I'm trying to implement for this demonstration. So I am planning to implement a concurrent cache, and basically there would be a couple of threads that will be writing certain values to the cache, and those threads will be reading the value from the cache, right? So how we could achieve this using the concurrent hash map is what we are going to build. So let's start. First we have the data structure that will be holding the cache, which is a map, of course, and it's a string. Let's call this as cache. This will be a concurrent hash map. Now let's implement the main method, and we are going to iterate from I as 0 to I9. So let's assume that this I value is the thread count. So maybe call this as thread number, and this is I. And what we will be doing is we will be creating a thread So let's create this thing anonymously. And finally we will also need to call start on this one. So we have written start here. So first thing is we create the key, and the key could be a key string at the rate of value and then the thread num. What we will do is we will try to fetch the same key 3 times so that we could demonstrate that one time the cache is empty, so we are going to put the value in the cache, and for the next 2 times the value should be fetched from the cache, right? So in order to mimic that functionality, let's write another loop. So from j0 to j less than 3, j plus plus, and let's capture the value, which is going to be, let's say, a method called as cached value. Let's pass the key. We will implement this get cached value in a moment. For now, let's just have this method name itself. Now let's print some message here. So the message could be thread dot current thread dot get name. Let me format this one, and let's say key, pass the key value, and value, pass the value. So this should be it for the main method. Now let's implement the other methods, which is the cached value for now. So let's call this as private static string get cached value. Let's say the parameter is the key, and what we do first is that we try to fetch the value from the cache. So cache dot get key. If the, let's correct this spelling. So if value happens to be null, it means that the key is not present in the map. So we need to calculate the key somehow, the value rather somehow. So let's have another method for the same. Let's call this as compute. Pass the key. It's not implemented. We will implement this in a while. Now let's put the same value in the cache. So cache dot put key, then the value, and finally return the value. All right. So let's implement the compute method as well, so that we can complete our entire implementation. So let's return this as a string. So compute, it takes a key, and first we print a message which is key not present in the cache. So I'm going to compute. Now let's put a try and catch block, because we will be needing this. So now what we are doing to implement here is that we have a compute method, and it's going to compute certain value. So we want to mimic the logic for computation, and so that will need certain time to execute. So let's mimic the same by putting a sleep here, maybe for 500 milliseconds, and once it's done, return the value, that is value for key. So I think this should be it for the entire implementation. Now let's run this one. So let me clean this up a bit. All right, let's run this and find out its output. So what we see here is that the thread get is started, and first is that key 5 not present in the cache, so going to compute. Then key 0 not present in the cache, so going to compute. So essentially for all the threads from 0 to 9, the key has been created, that is key at the rate of 5, key at the rate of 0, so on and so forth. And in the first try they are not present in the cache, so those will be calculated now, and once they are calculated they are getting fetched from the map itself, from the cache itself. So let's try to find this for key at the rate 5. So here 5 is being fetched, right? So for the first time it's being created by the compute method, and for the rest 2 times it's being fetched in this manner, wherein you have the thread 5 and the key is this one and the value is value for key 5. It's same for the other keys as well, for example for key 7, for key 6, for key 4, and so on and so forth. So what we have implemented essentially is a concurrent cache, and the idea is very simple, that there are a couple of threads which are going to put certain value in the cache and get the value out of the cache. How it's being done is like in the get cached value implementation itself, we are trying to fetch the value from the cache. If it's not present, we are computing it and putting in the cache. If it's present, then this will not be executed and directly we will be returning the value. So the first call to the cache is a cache miss, and then the cache will be populated with the value which is being generated by this compute method, which is doing nothing. It just has a sleep timer of 500 milliseconds, and then the value is returned as value for this particular key. And once the value is put in the cache, then for the subsequent calls the cache is being queried and we are getting the value from it. So as you can see that we have not used any locks or synchronization and all those things. So it's a very neat implementation because we are using the concurrent hash map, and this particular collection is a concurrent collection and we don't need to handle any sort of synchronization as such. So that should be it for the implementation and the code demo. Now let's learn a few more things about the concurrent hash map. So let's understand about the internal implementation and working of the concurrent map. Let's break this into 2 parts. The first is the adding an element to the concurrent hash map, and the second is fetching an element from the concurrent hash map. And why we are learning about the concurrent hash map itself? The reason is that it's the most commonly used implementation of the concurrent map interface, and for most of the use cases this should be sufficient for you as well. So let's learn how the elements are added to a concurrent hash map. So as the first step, we start with hashing and determining the segment. Internally, the concurrent hash map is arranged as smaller segments. When a new element is added to a concurrent hash map, its key is hashed to determine which segment it belongs to, and each segment acts like a small hash map within the larger concurrent hash map. In the second step, the lock is acquired. So once the segment is determined, the thread needs to acquire the lock for that segment. This ensures that only one thread at a time can modify that particular segment. And in the third step, data is inserted in this segment. With the lock acquired, the new key value pair is added to the segment's internal array. If needed, the segment may resize itself to accommodate the new element. And finally, as the fourth step, the lock is released after the insertion is completed. This allows other threads to concurrently modify the other segments of the map. And likewise, here are the steps that are needed for fetching an element from the concurrent hash map. So here as well, the first step is hashing and determining the segment. When a thread wants to fetch an element from the concurrent hash map, it first hashes the key to determine the segment which it belongs to. And as part of the second step, the activity is similar to adding an element. The thread needs to acquire the lock for the segment that contains the desired key. In the third step, we search in the segment. Once the lock is acquired, the thread searches for the key in the segment's internal array. Please note that since only one thread can modify the segment at a time, the search operation is safe from concurrent modifications. If the key is found, the corresponding value is returned. If not found, null or other designated value is returned to indicate absence of the element being searched for. And as the final step, after fetch operation is completed, the lock for that segment is released. Here onwards, other threads are allowed to access and modify the map concurrently. So this process continues over and over again for all the data writes and reads from the concurrent map, and this is how the concurrent map works in Java. So as we can see that here the locking and synchronization of the concurrent map is on a very granular level as compared to the approach of synchronization or creating the synchronized collection, wherein the synchronization was being done on the entire map or the entire collection itself. So this is pretty much faster in that sense because we are not holding up other threads from modifying or interacting with the map. And this is the reason that concurrent map is a better choice when you are dealing with a multi-threaded context and you need to have some sort of map-based collection. Imagine you are playing a game with a group of your friends. The rule states that everyone must gather at a certain spot before you can all move forward to the next level. This spot is like a checkpoint. Now, you cannot move forward until all your friends are there with you. In Java, this is like using the cyclic barrier. Each friend represents a thread in your Java program. When a thread reaches the checkpoint, it calls await method on the cyclic barrier. The thread waits there until all the other threads have also reached the checkpoint. Once everyone is there, the barrier is stripped and all threads can move forward. Now let's have a quick code demonstration using which we will understand how we can make use of the cyclic barrier in our Java program. So to demonstrate the cyclic barrier, let's create a class. I'll call this as multi-stage tour. The idea here is that I want to implement a feature wherein there is a group of tourists along with a tour guide, and there are different stages of the tour, and during a stage the tourists are supposed to arrive at a particular location, and once all the tourists arrive at a particular location, then they will move along to the next stage of the tour with the tour guide. So this is what we are going to implement overall. This is a small simulation to demonstrate the cyclic barrier uses. So let's implement the same. So first let's have the member variables. First we will have the number of tourists. So let's call this as public static final int. Let's say this is 5. Then the next one we could have as the number of stages. Let's say this is 3. And let's create the cyclic barrier. It's public static final. Let's call this as the cyclic barrier. Let's call this as barrier and new cyclic barrier. So cyclic barrier does accept a number, which is going to be the count on the basis of which it's going to maintain that how many threads have returned to the barrier point. So let's provide the same. And meanwhile, let's also check the other options that we have. So one option is this constructor. There is another constructor as well, which is giving us the integer value that we are supplying. The parties basically, and along with that we could also supply the barrier action. So what is the barrier action? So the barrier action is the command to execute when the barrier is stripped, or null if there is no action. So I think for demonstration purposes, let's include a small action for this. So let's provide a runnable here. And what we are going to provide is a simple message, that is tour guide starts speaking. So don't worry if it's not making sense as of now. As soon as I finish the implementation, I will explain everything in as much details as needed to understand this concept. So let's quickly create the static class as well, which is going to be the tourist class, and it's going to implement the runnable interface. Let's have the run method overridden, and it will have a member variable as tourist ID. We will initialize this tourist ID inside the constructor, and inside the run method, what we do is we iterate for the number of stages, and during each iteration we do some operation. So let's do that. So for int I as 0, I less than number of stages, I plus plus, and the first thing that we try to do is we introduce some sort of sleep in the thread. This is to mimic the activity being done by the tourist. So let's do it. So we will put this inside the try block. Let's have a sleep of 1000 milliseconds, and in the catch block, let's have the interrupted exception. Let's throw it as runtime exception for now. And once the tourist is done exploring the area, whatever activity they are trying to do in this particular time frame, then we are going to print a message. The message could be tourist, then the tourist ID arrives at stage, then I plus 1. So what we are trying to achieve is that in the given stage, the tourist comes, the tourist performs certain activity, that is the sleep for 1000 milliseconds. Essentially in 1000 milliseconds they do some activity, and then once they are done with their activity, we print this message that tourist with so and so ID has sort of completed their activity, and that is the reason that they are arriving at a particular stage where from we are supposed to move to the next stage. But catch here is that it cannot move to the next stage until and unless all the other tourists have arrived as well, and that is where we are going to make use of the cyclic barrier. So as I mentioned in the theory section, that we can call barrier.wait. So we will do the same. So let's put a wait here, and it expects us to provide certain error handling. Let's do that. And it's await, not wait. So let's correct it. And when we do await, then we will have to add another catch clause as well, that is broken barrier exception. Let's collapse this to one catch block, and this should be it for the run method. Now let's go to the main and implement it. So what we want to do is that for all the tourists that we have, that is 5 tourists, number of tourists, I want to create threads for each and every tourist, and then I want to start their thread. So let's do that. So for int I as 0, I less than num of tourists, then I plus plus. Let's create the thread. Let's call this as tourist thread, new thread, and new tourist. The thread ID could be I itself. Let's call the dot start on this one. So now let's run this and see the output. So here is what we are seeing. There is a delay of 1 second, and during that 1 second, all the tourists are there doing their activity, and they are arriving at stage 1. So once all the tourists have arrived at a stage 1, that is 0, 1, 2, 3, 4, then the tour guide starts speaking, and assume that this is the instruction about the next stage of the tour, right? And again the similar thing happens, wherein the tourists go to the second stage of the tour and they do their activity, and then the tourists arrive at the stage 2 before progressing forward for the next stage. And the same thing happens here as well. And since we have just 3 stages, this is where the tour stops. But the key thing to note here is that till the time all the tourists have not arrived, the tour is not progressing to the next stage. So essentially the tour guide or the tour group is sort of waiting for the time being until all the people in the group have arrived to a particular point, to a particular checkpoint. So that is what we have implemented here. Let's go through the code once. So first we start by initializing the number of tourists and number of stages. And we have a cyclic barrier. It's accepting two things. One is the number of parties involved. That is the number of tourists. So it's going to track 5 tourists, the 5 tourist threads. And then there is a runnable, which is going to print this message once the barrier is getting tripped or barrier is getting broken, right? And in the main, what we have done is we have just created number of tourist threads, and we are calling .start on them. And in the tourist class itself, which is implementing the runnable, the key area to look here is this run method, wherein for all the number of stages, what we do is first we allow the tourist. So you can visualize in this way that let's say that you are at the stage 1, and when you are at a stage 1, then you will be doing certain activity, and like you, the other tourists as well in the group, they would be also doing certain activity. And let's say everybody is doing certain activity in certain time range. So this is what is being mimicked by this thread.sleep. And once you and other tourists like you in the group, they are done with their activity, we print a message that tourist with this ID has arrived at the stage. And then we call the barrier.await. So let's say this is your thread which is being executed, then your thread will call barrier.await. And what this barrier.await will do is it will wait for all the other threads which are part of this group. So basically we have created this thread group, right? And this thread is having the same cyclic barrier, which is this particular cyclic barrier. And this cyclic barrier is being used by all the threads. So like you, there could be other tourists as well, and they would also be calling barrier.await. And essentially what will happen is until and unless not everybody in the group, that is all the 5 threads, have not arrived at this particular position, till that point of time the further execution will be halted. What could be the further execution? It could be anything. So this is the way in which this is going to work, and in this way we can make use of the cyclic barrier in our code. Please note that once the barrier.await is reached and once the barrier is broken, the barrier gets reset on its own. You don't need to do it explicitly or manually. So the barrier count is again initialized or reset rather with the initial value that you have provided, which is 5 in this case. So you could use it for the next round. So that's about the code demonstration. Now let's learn about how does cyclic barrier work under the hood. Under the hood, a cyclic barrier uses a combination of a counter and a condition to manage the waiting threads. When you create a cyclic barrier object, you specify the number of threads that must call the await method before the barrier is broken. Each thread that calls the await decrements the internal counter of the cyclic barrier. If the counter has not reached 0 yet, the calling thread enters a waiting state. So let's say the calling thread is you and you have called barrier.await, but what the cyclic barrier finds out that this internal counter is not reached 0 yet. So let's say to begin with it was 5 and then you called it, so it became 4. So it's not 0 of course. So what happens is you go into the waiting state, and when a specific number of threads have called the await, the barrier is tripped. So let's say that after you, other 4 threads came in and they also called barrier.await, and eventually the value of the count, internal count, became 0. So at this point all the waiting threads are released and they can proceed with their execution. So that is where all the waiting threads, that is you and the other 4 threads, will be released. They will be notified that they could come out of the waiting state. And after the barrier is stripped, the internal counter is resets to its initial value. And the barrier is ready to be used again for subsequent synchronization points. This reusability distinguishes Cyclic Barrier from the countdown latch, which cannot be reused once the count reaches 0. So this is pretty much about the Cyclic Barrier and the way in which we can use it. And we also learned about how does it work internally under the hood. So that's all about the Cyclic Barrier. Now let's learn about the exchanger. In Java, an exchanger refers to a synchronization point at which threads can pair and swap elements within a concurrent environment. The Java util concurrent exchanger class facilitates this functionality. The way this works is that two threads can call exchange method on the exchanger object, passing the object they want to exchange. Why and when to use exchangers? Exchangers are useful in scenarios where two threads need to synchronize and exchange data before proceeding with their respective tasks. For example, imagine you have a pipeline of processing steps and each step is executed by a different thread. In such a case, you might want to use an exchanger to exchange data between adjacent steps in the pipeline. So, how is exchanger implemented in Java? Exchanger is part of Java util concurrent package. Exchanger is a class and it does not implement any interface or extend any class. Also, exchanger is not implemented by any other class in Java. It is a standalone class which is specifically designed for synchronizing the exchange of data between two threads. The class has two important methods. First is exchange, which takes an object, and this method is used to perform a blocking exchange operation. It waits until another thread arrives at the exchange point and then exchanges the object X provided by the current thread with the object provided by the other thread. It returns the object provided by the other thread. If the other thread has not arrived yet, the current thread will block until it arrives. The other method is the exchange variation. It's an overloaded method which is going to accept an object, and other than that, it will also expect us to pass a timeout. It's similar to the above one, except it has a timeout parameter. If the other thread has not arrived at the exchange point within the specified timeout duration, a timeout exception is thrown. Now let's have a quick code demonstration which will show us how we can use exchanger in our code. So here we are in the concurrent collection package. Let's create the class. Let's call this as exchanger demo. So what we are going to implement is two threads. Let's call them as first thread and second thread. And then they will have an exchanger at their disposal using which these two threads will be exchanging certain information with each other. So let's start by implementing the first thread. Let's call this as class first thread implements Runnable. So let's implement the run method. It will have the exchanger and it's a generic class, so we will have to pass the type. Let's say we pass the type as integer. Let's name this as exchanger. Let's initialize this exchanger inside the constructor. And in the run method, let's have a data to send variable with a value 10, and we will print this value. So first thread is sending data to send, and now let's call exchanger dot exchange and pass the data to send value. This will return a value, and let's capture that as part of variable which we could call as received data. And exchange will expect us to handle some exceptions. Let's surround this with try catch. And once we have received the data, let's print it out on the console. So first thread received data. Now let's implement the second thread as well. And once we are done with the implementation, we will see how it's interacting with each other. So let's call this as second thread implements Runnable. Let's have the exchanger here as well, and we will pass the integer as the generic type. Initialize this particular exchanger in the constructor, and in the run method, let's start by having a sleep of, let's say, 3 seconds. And here as well we have a data to send variable with a value 20. We will print some sort of message. Second thread is sending data, and let's say data to send, and then exchanger.exchange. Let's pass the data to send. Let's capture this as part of received data, and let's print this on the console. So second thread received and received data. Let's handle these exceptions. Try catch. And what we can do is we can also capture this and place inside the try block. So we should be good with the implementation of the second thread. Now let's implement the demo class, and in order to do so, let's have the main method. In the main method, let's have the exchanger, new exchanger, and we will be creating 2 threads. So first one, new thread, and first thread, let's pass the exchanger because the thread is going to expect us to pass the exchanger object. Let's do the same for the other thread as well. Let's call this as 2. We will start these two. So 1.start, 2.start. So this should be second thread. Now we will run this and see the output. So we can see that we are seeing first thread is sending data and second thread is sending data, and second thread received 10, that the first thread is sending, and the first thread received 20, that is the second thread sending. But there is a key information that we must notice. Please note that in the first thread we are sending the data right away, wherein we are calling the exchanger.exchange. But in order for this exchanger.exchange to be executed, the other thread should be able to receive it. That means as long as the other thread is not calling its exchanger.exchange, then in that case this thread will be blocked. And what we are seeing in the second thread is that before calling exchanger.exchange, we are putting a sleep of 3 seconds. So that is the reason we are observing a delay, because thread 1 here is blocked for 3 seconds, because when the execution comes inside the second thread, it's sleeping for 3 seconds before calling the exchanger.exchange. And once the execution comes here, then it means that thread 1 will be sending its data, that is data to send 10, and that will be received by the second thread and captured in the received data. And likewise exchanger.exchange calls this data to send, and this data to send value, that is 20, will be received by the first thread, which is captured by this received data variable, and the same will be printed with this value, that is first thread received data. So let's run it one more time to observe the blocking nature of the exchange method. So we can see that first thread is sending data and there is a delay before all of these things are executed. So we called first thread is sending data, then exchanger.exchange was called, and because the second thread went into the sleep for that amount of time, that is 3 seconds, the first thread got blocked, and as soon as the second thread is active, the exchange happens and the first thread receives the data to send value from the second thread, which is 20, and likewise the second thread is receiving the data from the first thread, which is a data sent value of 10. So this is it for the code demo. I hope it would have somewhat cleared your doubts with respect to how exactly can we use Exchanger. Now back in the theory section, let's do a quick comparison between the queue and the Exchanger. So you may feel that a queue could achieve similar kind of synchronization between the threads, right? And yes, you are partially correct in thinking so. However, the choice between using an Exchanger and a queue depends on specific requirements of the synchronization pattern which you are trying to implement and the characteristics of your application. So here is a quick comparison. The Exchanger facilitates a direct exchange of data between two threads at a synchronization point. Each thread waits until both the threads has arrived at the exchange point before proceeding. If you have exactly two threads that needs to synchronize and exchange data, the Exchanger provides a simple and efficient mechanism to accomplish this. Exchanges occur synchronously, meaning both the threads wait for each other at the exchange point. Both threads exchange data of the same type and quantity, making it suitable for symmetric communication patterns. The queue, on the other hand, however, is different from the Exchanger in these parameters. So the first is that queues are more versatile and could handle communication between multiple producer and consumer threads. And depending on the queue implementation, producers and consumers may operate asynchronously. Producers can enqueue data without waiting for consumers, and consumers can dequeue data without waiting for the producers. Queues can act as buffers, allowing producers to continue producing data even if consumers are not immediately available to process it. And in some cases, the exchange may not be symmetric. However, the Exchanger is very similar to a type of queue that we saw earlier, and that type of queue is called as synchronous queue. So both synchronous queue and Exchanger facilitate blocking synchronization between threads. However, while a synchronous queue is unidirectional, the Exchanger happens to be bidirectional. So with the use of Exchanger, you could achieve a bidirectional data exchange between two threads, which means when you do call .exchange data, at one hand you are sending certain value, but you are also receiving certain value from the second thread as well. So that is the bidirectional nature of the Exchanger. So that should be it for the topic of Exchanger. Now let's learn about the copy on write array. Copy on write array is like having your own copy of book to read. When someone wants to write in the book, instead of disturbing your reading, they make a new copy. This way, you can keep on reading without any interruptions. You can use copy on write array when you have multiple threads accessing and modifying data at the same time. It ensures that readers don't get disturbed by writers, and writers don't interfere with each other, making your program safer and more efficient. Let's have a code demonstration which will tell us how we can use copy on write array in our Java code. We are in the concurrent collection. Let's create a class and let's call that as copy on write array demo. So what we are going to implement is two threads. One is the read task and the other one is the write task. And as the name suggests, that read task is going to read something and write task is going to write to something, and what it's going to read and write from is the copy on write array. So let's start the implementation. Let's create the read task, and this will implement a runnable interface. Let's implement the run method, and let's have a list of integers. Let's call this as list. The type would be integer. Let's name this object as list, and we can initialize this using a constructor. And what we want to do inside a while loop is we want to put some sort of sleep to the thread and then print the list. So that is going to mimic the infinite reading operation. So let's do that. So while true, let's call the thread.sleep, and maybe it could be for 1 second. Let's do the exception handling, and once it's done sleeping, we will be printing the list. So that's about the read task. Now let's create the write task, and it will implement a runnable. Let's implement the run method, and this as well is going to expect us to pass a integer. So let's do that, and let's have a random generator, and we could have a constructor. For the random, we could just say new.random, and in the run method we are going to do two things infinitely. First is we will wait for certain time. Second is we will be writing certain value to the list. So let's do that. So let's have the while loop, while true, thread.sleep. Let's have this for 1200 milliseconds. Let's handle the exceptions. And outside the try catch block, let's call list.set random.next integer, and it's going to be in the size of list, and then random.nextInt, and the upper limit is going to be 10. So what we are doing essentially is that we have a list, and in that list we are picking any random index, and on that random index we are setting any random value that is in the range of 0 to 10. So that's about the write task. Now let's write another class that is going to mimic the simulation that we are trying to do. So let's call that as simulation. Let's have the list. Let's call this as private final list integer list, and let's create the constructor. So what we want to pass instead is new copy on write array list, and let's remove this one because this is not needed now. And to this list I want to add certain values. So arrays dot as list, and let's pass some zeros. Alright, so we have basically instantiated a list, made that as a type of copy on write array, and in that particular copy on write array we have provided some values which is all zeros. Now let's have a method, call that as simulate, and what this thing is going to do is it's going to create certain threads. So first could be new write task. Let's pass the list. Let's duplicate this. This one could be 2, this one could be 3, and this one could be 4. This as well could be a write task, this as well could be a write task, and let's have this one as a read task. So basically we have 3 writer tasks and 1 reader task. Finally, let's start these. 3.start, 4.start, and in the main class, let's have the main method to begin with, and we will create the object for simulation, new simulation, and then let's call simulation.simulate. So let's go through the code once before we run this. So what we have done effectively is we have created 4 threads, 3 out of which are the writer threads and 1 is a reader thread. What the writer thread is going to do is it's going to run infinitely, and every 1.2 seconds it's going to set certain value in the list that we are going to provide, which is specifically the type of copy on write array. And the way it's going to write is it's going to pick any random index and going to place any random value. And what the read task thread is going to do is it's going to execute infinitely, it's going to run infinitely, and in every run it's going to sleep for 1 second and then print the list. And finally we are running all these threads, and this is basically we are creating the object and calling the simulate method, which is going to do all of these things. So now let's run this and see the output. So you could see that to begin with we have this array, then the writer thread wrote something, and then that is being read by the reader thread. So it keeps on happening that the writer thread will be writing something to the array that is pretty much random, and then the reader thread will be reading from the array. The point to note here is that this is being done in a multi-threaded context and we are not leading to any exceptions. For example, any modification exception or any kind of inconsistency. So situations like this, when we should have copy on write array list, and this particular data structure will help us in ensuring that an array list is being used in a multi-threaded environment without any of the synchronization or concurrency concerns. Now let's learn a few more things about the copy on write array. So now we will learn how it works. So when a thread wants to read from the array, it creates a snapshot of the array and uses the same to read. If a thread wants to write, it also creates a snapshot of the array and performs the write operation. Once the write is completed, the changed array is considered as the latest version of the array, from which snapshots could be created for the read and write operation. This way, readers don't see the changes until they get a new snapshot. It ensures that they always have a consistent view of the data. So we could loosely draw parallels between the Git branching approach and the way in which copy on write array works. Each modification to the array creates a new version, much like creating a new branch in the Git. Just as Git would allow for parallel development without conflicts, copy on write array allows for multiple threads to modify the data concurrently, and it does so without interfering with each other. And just as Git consolidates changes during the merging, copy on write array eventually consolidates the modifications into a single reference version. This version ensures data consistency. Both systems provide a structured approach to managing concurrent changes. So I think it would make sense to visualize what we just discussed. So let's do the same. So let's assume that this is our array and it has certain values as in 3, 5, 1, 2, and the first call on this array is a read call. Imagine this line to be the reference line and consider that this line has the latest value of the array. So whenever a read or a write operation is supposed to be done, those operations are going to create certain snapshots. So the first call that we are getting on this array is a read call. So as soon as we have a read call, a snapshot of this thing is created and the read will be performed on this one. So what effectively happens is that even though if there is any write operation that is going to happen, it won't impact this value because we have taken a snapshot of this particular array at this particular time. Since this line is the source of truth during creating a snapshot, the same value remains to be seen here. And this is the array from which the read operation will be served. Now let's say going forward at this point of time, a write operation is invoked. What it says is that write a value 4 at index 2. So since this latest value or the reference value has this array that is 3512, a snapshot is created which is 3512, and on this snapshot the write operation is applied. So as soon as the write operation is applied, the array changes and the value becomes 3542, and the same value would be written to this source of truth or this line or this reference, right? So let's say we have a read operation now, and this read operation comes after the update has been written. So since this reference has this value of 3542, the read operation is again going to create a snapshot, and now the snapshot will contain this value 3542. So when the read operation is served, the same value is returned, that is 3542, and this process keeps on happening. So you see, what we have is our reference value to begin with and a line which is serving as a source of truth, and whenever we are going to have any read operation, we are creating a snapshot, and whenever we are having a write operation, we are creating a snapshot, and after that write operation is complete, then the same is merged back to the main line. So that is the reason I told that it is somewhat similar to the way in which Git branching works. So you could consider this as the master branch, and read is anyway read. It's not going to write anything or impact the data, but still we want to avoid a situation wherein the master branch could change during the read is being performed. So that is the reason a snapshot is being created to serve the read as well. But it's very evident that in the write scenario, another branch is created, and on that branch whatever writes are supposed to be done, those writes are done, the 4 in this case at index 2, and once this is done, once it is successful, the same thing is written back to the main line, to the main branch, and once this thing is merged, now the main branch has this particular value, that is 3542. So this is the way in which you could visualize the write on copy array, and I hope that it will help you in understanding this concept in a much better way. Locks are an important topic in Java. So let's learn about the locks. What exactly are locks? Well, imagine you have multiple threads running simultaneously in your Java program, and all are trying to access the same resource. Without proper synchronization, it could lead to inconsistency in data and other chaotic situations. That's where locks come in handy. Locks provide a way to control access to shared resources, ensuring that only one thread can access the resource at a given point of time. Thus, it helps in preventing data corruption and other concurrency issues. You may wonder that it's sounding very similar to what the synchronized blocks do. Well, you are right in thinking so. So now let's learn the difference between using synchronized blocks versus the locks. In Java, when it comes to managing concurrent access to shared resources, two commonly used mechanisms are available. These are synchronized blocks and locks. Let's start with the synchronized blocks. Synchronized blocks use the synchronized keyword to ensure that only one thread can execute a particular section of code at a given point of time. They provide intrinsic locking, which means that the lock associated with the object is acquired and released automatically by the JVM. Synchronized blocks are easy to use and require less boilerplate code compared to the locks. However, they have limitations, such as lack of flexibility in lock acquisition and inability to handle the interrupts. On the other hand, locks provide more flexibility and control over locking mechanisms. Java lock interface and its implementations allow to manually acquire and release the locks. Moreover, you could acquire and release the locks in any sequence and in any scope, which is not possible if you use synchronized approach. So, when you should use synchronized blocks versus locks. Use synchronized blocks for simple synchronization needs, where flexibility and performance are not that critical. Use locks for complex synchronization scenarios, where fine-grained control and flexibility are required. In conclusion, both these synchronized blocks and locks are essential tools for managing concurrent access to a shared resource in Java. Understanding their differences and choosing the right synchronization mechanisms for your specific requirements is a crucial part of writing a robust and efficient concurrent code. So, now it's time to learn how can we implement and make use of locks in our code. While doing so, we will also learn about a couple of important concepts related to locks such as conditions, different types of locks, etc. Till now, we have learned that locks are an important part of implementing the concurrency in Java. But we also need to have some sort of interaction between the threads and locks. So the mechanism which helps us in managing these interactions is called as condition. Let's understand what are conditions with a very simple and easy to understand explanation. Here I would request you to make a very weird assumption which could help in avoiding any confusion with the terminology of lock. Assume that lock here is the key as well. What I mean to say is, when you have access to the lock, the door which is guarding the protected resource is unlocked magically, and thus the lock is a key as well in that context. Hence, as soon as you acquire the lock, you get access to the resource. Please note that only one person is allowed to access the resource. No one else can tailgate behind you. With this in place, let's learn further. A lock in Java can have its own set of rules. These rules are called as conditions. Effectively, this means that a lock could have more than one condition associated with it. Conditions help us in controlling how threads interact with the lock. You could visualize threads as people who are trying to access some protected resource, and think of condition as a waiting room attached to the lock. Imagine a person comes up and tries to get hold of the lock, but lock is being held by some other person. Thus, this guy won't be able to acquire the lock. So what he does instead is, he goes to wait in this room where other people may also be waiting for the lock to be available. Inside the waiting room, people wait until someone signals that it's their turn to use the lock now. This signal could come from a person that is currently holding the lock or from some other source. So, who gets the chance to acquire the lock? Well, that's something which depends on the implementation. The key takeaway from here is that after a signal is given, any one person from the waiting room is allowed to acquire the lock and do their processing. In Java, these conditions help in managing the interaction between threads and locks. Now, let's visualize how conditions work. Imagine there are two threads, thread 1 and thread 2. To begin with, thread 1 is executing something. However, it cannot move forward until some particular condition is met. This condition could be anything based on your use case. For example, a queue being full could be a condition. In this case, as soon as the thread cannot move forward, it will call condition.await. If you read this from the right, it appears as if a thread is saying that I am waiting for this condition to be fulfilled. So, I am awaiting for a given condition. Effectively, the thread 1 goes to a waiting state. Now let's imagine there is another thread, thread 2, and this thread is running and doing some operations. Due to the operations being performed, the condition gets fulfilled, and as soon as the condition gets fulfilled, this thread 2 calls condition.signal. It signifies that the condition has been fulfilled, so convey this message to any of the threads which have been waiting for this condition to get fulfilled. As soon as the signaling happens, JVM finds all the threads which are in the wait state anticipating this condition to be fulfilled and wake the one which has been waiting the longest. In this example, there is only one thread which is thread 1. So the state for thread 1 goes from wait state to the runnable state. So the thread 1 which was blocked at this point of time is now active from this point of time. because at this point of time, thread 2 signals that the condition for which thread 1 was waiting, it has now been fulfilled. So thread 1 could proceed with its processing. Now let's analyze this scenario where we call condition.signalAll. Like we had condition.signal, there is another method signalAll. So in this example, we have 3 threads, and during its execution, thread 1 calls .await, and after some time, thread 2 also calls .await. There is another thread which is thread 3, and during its execution, the condition for which thread 1 and thread 2 are waiting gets fulfilled. So the thread 3 calls condition.signalAll. As soon as signalAll is called, all the threads which are waiting for the condition to be fulfilled are waked up by the JVM. JVM pulls them out of the blocked state and moves them to the runnable state. So depending on the number of cores your CPU has, threads could be scheduled for execution accordingly. So if .signal was called instead of signalAll, thread 1 would have been waken up, since it's the one which has been waiting for the longest. So this is the way in which condition helps us into maintaining or managing the interaction between the threads and the locks. There are 2 methods, that is signal and signalAll, which are used to notify that a particular condition has been fulfilled, and there is one method which is condition.await, which is used to hint that a condition needs to be fulfilled before a given thread could proceed further in its execution. In case if you are wondering that condition methods discussed above are very similar to the wait and notify methods in the object class, you are correct. Indeed, these methods are similar to wait and notify. The main difference, however, is that conditions provide a much granular control over the synchronization of the protected resource. Now, with that in place, let's have a quick code demonstration which will teach us how can we use the conditions and its related methods. Let's create a package, and we can call this as locks, and let's create a class, call this as condition demo, and here is what we are going to build. So basically we are going to build a producer consumer implementation using the locks and conditions. So let's start. So first thing that we will have is a max size, which is the number of elements that could be kept in a buffer, which is going to be a queue. So let's have that. So it would be private final integer max size. Let's have the value as 5. The next thing is we will define the lock. So lock, and the type of lock that we are going to use is Reentrant lock. So Reentrant lock is one type of lock in Java. We will have to create the queue or the buffer where we are going to place the elements. So let's create the queue. Let's call this as buffer, and this could be of type linked list. So basically from this buffer, the consumer will be consuming and the producer will be writing to it. Next, we will be creating certain conditions. One condition would be that buffer not full, and the other condition is buffer not empty. So let's create the same. So private final, this is condition, and buffer not full lock. The way to create the condition is to call the .new condition method, and we will do the same for the other condition as well. So this condition could be something like buffer not empty, and we could have lock.new condition. So we will have 2 methods. The first one is producer. So private void produce and int item. So let's have this, and so what we will be implementing is the produce section of the implementation, and we want this to be synchronized. While this particular code block is getting executed, we don't want something else, or let's say some other thread, to come and work on this simultaneously. So the order to do this is, first we will have to acquire the lock, and the way to do this in Java is called log.lock. And once we are done with our processing, finally we need to call log.add. unlock. So this looks fine, but there is a problem. Let's say when the processing is under the way, there is some exception which happened. So in that case, the code will terminate then and there itself, right? The lock.unlock will be never executed, and the other threads which are waiting for this lock will go into a state of deadlock, and that is not good. So the way to do this is call this lock.unlock in the finally section or the finally block. So in either case, this lock.unlock is always executed. So this is a common pattern which we use while making use of the locks in Java, and this is the way to implement this. So let's have the try block, and here we will put the processing, right? And we will have a finally block, and that is where we call the lock.unlock. So with this in place, let's implement the processing part. So here is what we are going to implement now. First we will check if the buffer is totally full. Then for that duration, we will have to make the producer thread wait. Otherwise, we will put some item in the queue, and then we will notify if there is any consumer thread which is waiting for the producer to put certain item in the queue. So let's implement this. So we start by checking if the buffer size is equal to the max size, which is 5. If that is the case, then we have buffer not full, and on this condition this thread will wait. After that, we will add certain item to the buffer, and next we will have a print message which says something like produced, and produce this particular item. And for the buffer not empty, we are going to put this signal. So let's also complete the consumer method, then we can have a complete look over the entire implementation. So let's have private void consume, and like the produce method, it's also going to throw an interrupted exception. So let's have that in the method signature. We start by acquiring the lock, so lock.lock, and we will follow the same pattern that we saw earlier, that we will have a try and finally block, and in the finally we call the unlock method, and in the try we have the implementation. So here we will check if the buffer is empty, and if it's empty, then we call buffer not empty and await on this condition. And if this is not the case, then we are going to consume from the buffer. And the way we do this is we print a message which says consumed, and from the buffer we take out the element by calling the dot pole, and next we call a signal on the buffer not full. So this is the consumer method. So you may have a doubt here. What you may think is that the nomenclature of buffer not full and buffer not empty is kind of misleading and confusing. So I totally understand that, and I also had this confusion for quite some time. But the way to interpret this is that this nomenclature should be understood from the perspective of this signal. So the condition is buffer not empty. So what it means is that this buffer not empty condition is being awaited by certain thread. And which thread may await this? The thread which may await this is this one, right? That is going to consume. So if it's consuming, then at that point of time, it needs to have something in the buffer. Otherwise, there is nothing to consume. So that is the reason if the buffer is empty, then on this particular condition, this consume method is going to wait. And let's say if it's waiting for something to be put in the buffer, and then the producer method is executed by some thread, the producer thread, then at that point of time, something was put in the buffer, some item was put in the buffer, and that is where once we have put something in the buffer, we are going to call this signal. So what essentially we are saying is that buffer not empty condition is going to signify that something needs to be there in the queue for the consumer to consume. and that is the reason consumer is going to wait on this condition, that is buffer not empty. Likewise, we have buffer not full. So buffer not full is being signaled by the consumer, and the idea remains the same, right? So when producer is producing something, then it needs to ensure that the buffer is not full, and if it's full, then it will have to await. And this condition is being signaled by the consumer, and what it means is once the consumer has consumed something, then there is certain space in the queue, in the buffer, in which the producer could produce. So that is the reason if there is a producer which is waiting for this condition, then this particular thread, the producer thread, will be awakened when this buffer not full is signaled. So that is the idea, and that is the intention behind this nomenclature and behind this implementation. Now let's complete this by writing the main method, and then we will have a code demonstration by running the code. So let's implement the main method, and let's have the condition demo object created. So new condition demo, right? And let's have the producer thread. Let's call this as producer thread, and let's have a try block and have a catch block as well. So when we call producer, it's going to throw that interrupt exception, so that is the reason we need to have it. And we are also going to introduce some sort of sleep, so that will be handled by the catch block itself. So what we are going to do is we are going to run this producer thread for 10 times, and we call the demo dot produce and pass I in this one. So I is the item that needs to be put. So essentially this producer thread is going to put 10 items in the queue, in the buffer. Next, let's have the thread dot sleep, maybe for 1 second, and in the catch we have a runtime exception, which is this E. So this should be for the producer thread, and for the consumer thread, let's have another one. First, let me rename this one to consumer thread, and again we will have the similar pattern. We will have a try and catch. Let's have the interrupted exception, and let's throw the runtime exception. And what we do is we are going to call consume 10 times. So I less than 10 and demo dot consume, and we are going to put a sleep for, let's say, 2 seconds. And once we have this thread created, we will have to call the dot run on these two threads. So first is producer thread dot start, then consumer thread dot start. So that should be it from the entire implementation perspective. Now let's run this and see the output. So you see, we have a demonstration, a simulation of the producer consumer problem. So produced 0, consumed 0, produced 1, consumed 1, and produced 2, produced 3. So remember, we had put a sleep timer of 1 second in the produce method and 2 seconds in the consume method. So in that sense, consume method is on the slower side, and that is the reason here we have the producer producing something twice, and consumer is kind of on the slower side. So we are producing twice and consumer is going to consume something once, right? But this pattern is not something which is very deterministic. The entire idea behind having that sleep was just to showcase the demonstration in somewhat presentable manner, right? So that should be it for the conditions in Java. And please note that these conditions could be only derived from the lock interface implementations, which are Reentrant Lock, read write lock, and any other implementations which you could explore in the JDK. And these conditions are not available for the locks that we have on the object level, the implicit locks which are available with the object in Java. Now let's learn about the Reentrant Locks. Reentrant Lock is one of the many implementations of lock interface in Java. It allows a thread to acquire the same lock multiple times without causing any deadlocks. What this means is that a thread which holds a lock can acquire it again without blocking itself if the lock is reentrant. In contrast, with a non-reentrant lock, an attempt to acquire the lock again within the same thread without releasing it first would typically result in blocking. It could also potentially cause a deadlock situation if it's not handled properly. How does this work? The way this works is that the locking mechanism keeps track of the lock being held by a thread. In the case of non-entrant locks, attempting to acquire the lock again within the same thread typically results in blocking the thread. However, in the case of reentrant lock, the lock mechanism allows the same thread to acquire the lock multiple times without blocking itself. Effectively, the held count for the lock by the given thread is incremented. Since the lock is already acquired, there is no sense of reacquiring it. This is achieved by maintaining a count of how many times the lock has been acquired by the same thread. The lock is only released when the count reaches 0. It indicates that the thread has released the lock the same number of times it has acquired it. You may be wondering why and in what situations a thread would need to acquire a lock again without releasing the lock. Here is the answer. Imagine a scenario where a thread invokes another method or code block which also requires the same lock to maintain consistency in the multi-threaded context. This pattern is quite common in complex implementations where methods call other methods within the same class. These methods require synchronized access to some shared resource, and in such situations, reentrant locks are quite useful and in fact very much needed. So with that in place, let's have a very quick code demonstration of using the reentrant locks. So to begin with, I have created this class called as Reentrant Lock Demo, and here are the two fields that we are going to need. So in this line, we are initializing the reentrant lock. The way to do this is by calling new reentrant lock. There are other variations of this particular constructor wherein we could pass the fairness criteria and all those things. We will learn about those in a while. So for now, we have created the lock, and then we have a variable called as shared data, which is initialized to 0. Next, we have a method A. What this method does is it's going to increment the value of the shared data, and then it's going to call another method, which is method B. And method A needs to get hold of the lock for this section of the code block, that is incrementing the shared data and then calling the method B. And finally, this particular lock is released. Now let's see what we have in the method B. So in the method B, again we are going to work on the shared data, and the way it's being implemented is the shared data value is getting decremented, but we need some sort of lock, and that lock is going to protect this particular section, which is decrementing the shared data and printing the value. And finally, we call the unlock method. So what we see is that we have a method A which is getting called by some thread, and it's going to acquire a lock, but in the same block, when it's being protected by the lock, there is a call to method B, and that method B as well is going to need that lock because that is also handling some sort of critical section. So this is the reason that we have made use of the reentrant lock. So this particular thread is already holding this lock, but at this point of time, this will need to acquire the lock again. And if it was not a reentrant lock, we could have encountered a blocking scenario, and that could have also led to a deadlock. So that is the reason we have used the reentrant lock. Now let's see the further implementation. So we have a main method, and what we are doing is we are creating and starting multiple threads, which are essentially 5 threads, and we are calling the start on those. So Let's try to run this and see the output. So here is the output. That method A had shared data as 1, method B had shared data as 0, method A and method B, so on and so forth. So the key takeaway is that we are able to deal with the shared data value in a concurrent environment, in a concurrent fashion, in a multi-threaded context. And the same thread is going to need to acquire a lock multiple times, and that is the reason we have used the reentrant lock. So at any given point of time, let's say here, if you would have called lock.getHoldCount, then the value would be 2. So essentially what is happening is the first time the lock is acquired here and the second time the lock is acquired here. So essentially this thread has acquired this lock twice, but under the hood, of course, it has been acquired just once. It is just the count which is getting incremented, and which is 2. And finally this lock will be unlocked, it will be released, so the count will become 1, and then the call comes here, and finally this lock.unlock will decrement the value further and it will become as 0. And that is where we will conclude that the given thread has released this particular lock. So that is for the code demonstration. Now let's look further into certain other aspects of reentrant lock, which is the lock fairness. So reentrant lock provides a constructor in which we can pass a boolean value for the fairness of the lock. When this value is true, the lock is called a fair lock. If it's false, it's called as an unfair lock. By default, the reentrant locks are unfair. Let's understand this fairness with an example. Imagine there are a couple of threads which are trying to acquire a lock. Among all the threads which are competing for the lock, let's say thread 1 gets hold of the lock. All the remaining threads go to some sort of waiting queue. After a certain time, thread 1 releases the lock by calling the unlock method. At that point of time, one of the locks in the wait queue will get a chance to acquire the lock. Imagine that out of all the threads in the wait queue, thread 2 has been waiting the longest for acquiring the lock. Then, if the reentrant lock is fair, thread 2 will get a chance to acquire the lock and do its processing. In the case of unfair reentrant locks, there is no deterministic guarantee as to which thread gets to acquire the lock. As a sweet side effect, the unfair locks could potentially provide a better performance as compared to the fair locks. What is the reason? Well, they avoid the overhead associated with maintaining a wait queue and enforcing some sort of deterministic ordering. Now let's learn about a few important methods of the reentrant lock. The first one is getHoldCount. This method returns an integer which is the number of times the current thread has acquired the lock. In other words, it indicates how many times the current thread has successfully acquired the lock without releasing it. The next one is the try lock, and as the name suggests, it is an approach where we request a thread to try acquiring a lock. Result is a boolean which tells if a thread was successfully acquired or not. If the outcome is true, we can proceed with processing, and if false, we can do something else. And what we gain from this approach is, if the lock has not been acquired, then we are not blocked. Rather, we can do some sort of other processing as well in our code. There is another variation of try lock method which accepts timeout and time unit. So this is an overloaded variation of the try lock method. Using this method, we can request a thread to acquire the lock and be blocked for the given time duration. If the lock is being held by some other thread, we hope that the lock becomes available during the waiting time period. And that's where the lock is acquired by the thread which has called the try lock with duration. And if not, then of course the output of this particular try lock is a false, and then we can do something else because we have not acquired the lock due to X and Y reasons. Well, try lock has a problem. Even if your reentrant lock is fair and try lock is called by a thread at the moment the lock is released by some other thread, in this scenario, the waiting threads for this lock are not given the priority. The new thread which made the try lock call gets to acquire the lock. The workaround for this problem is to pass a timeout value of 0 time units, and this will ensure that the fairness criteria of the lock is honored. Then we have a couple of auditory methods. So we have something like is held by current thread. and it returns a boolean which tells if the current thread is holding a given lock or not. The next one is get queue length, and it tells the length of the wait queue, which is the number of threads. These two in particular are mainly used for debugging and profiling purposes. But having said that, if there is a need in your code implementation or in your business logic, you could surely have these methods at your disposal. The final one in our list is the most important one. So the new condition, as we saw earlier, this returns a condition on the given lock. And what it does is it helps in orchestrating the interaction between the thread and the lock. So that should be it for the reentrant lock. In Java, a read-write lock is a synchronization mechanism which allows multiple threads to read a shared resource concurrently, but only one thread can write to the resource at a time. This mechanism is particularly useful when the resource is predominantly read-heavy rather than write-heavy. Let's understand this by visualizing an example. Imagine that there is a booking system using which you could book seats in a bus. There are two main functionalities when it comes to the seat selection. First is you should be able to view the available seats, and the other one is where you can book a particular seat. So in the image that we have threads from 1 to n which want to view the available seats and threads from 1 to n which want to book a seat. As per what we have learnt already, for any thread to be able to do some processing, it needs to acquire the lock. So let's assume that thread 1, which wants to just read the seat availability, acquires the lock and proceeds with it. Please note that this is not efficient. Why so? It is because there are other threads which also wanted to just read the data. Since they are not writing anything, there would not be any concurrency issue involved if more than one threads acquire the lock and do its processing. And this processing is just to read the data. So how about if we could somehow club the reader threads together, and it would be much efficient, right? And yes, certainly it would be very much efficient, and the read-write lock indeed does the same thing. After some time, the read threads are done reading the data, and at some point of time, the read lock is released. Once released, either of the writer threads could acquire the write lock and do their processing. Effectively, in the case of a read-write lock, one writer thread could get hold of the writer lock at a time, or multiple reader threads could get hold of the read lock at a time. Please note that we have two locks, one for the reader, other for the writer. So even though we have two different locks, two different objects, only one can be acquired by a thread or a group of threads at a given point of time. So either read lock is used by n threads or write lock is used by one thread, but it can never happen that both the locks could be used at the same time ever. So what we have seen essentially that there are two kind of threads. The first category is that of the reader threads. The second category is of the writer threads. Since reader threads are not mutating anything in the data, they are safe to run together. And that is the reason that all these reader threads could acquire the reader lock at once and do their processing. When it comes to the writer thread, this could not be the case because writer thread is going to change something to the data. And that is why only one writer thread is allowed to acquire the lock. So in such scenarios wherein you have a very much clear condition of reader versus writer, this is one such lock which could be used in such cases. And please note that you would gain performance if your application is, or rather if your use case is read heavy, not a write heavy. So now we will have a quick code demonstration to see how can we make use of the read write lock. So as part of the code demonstration, what we are going to build is a class which will have a counter. There would be a couple of reader threads and a writer thread. The writer thread will try to increment the value and the reader threads will try to read the value, and we wish to do so using the read write lock. So let's implement it. We will create this class in the logs package. Let's call this as shared resource, we will have a variable, let's call this as counter, the value is 0. Then we will have the read write lock, so read write lock, let's call this as lock, and we will be instantiating the object of new reentrant read write lock. We have the first method which is supposed to increment the value, and the way we do this is we acquire the lock, so lock dot write lock dot lock, and we will have the implementation inside a try block. Finally is used to unlock the lock that we have acquired previously, and what we will do is we will increment the counter by calling counter plus plus, and we will print a message. The message could be something like thread dot current thread dot get name, and it writes and the value, that is counter. So this should be it for the increment method. Now let's implement the other method as well, which is going to get me the value of the counter in a given thread, and idea is that this is supposed to be made use of by the reader thread. Let's minimize this one. Now back to the implementation of the get value. First we try to get hold of the read lock and call lock on this one. Next we will have the try block, and inside the finally we will close the read lock that we have acquired by calling the unlock method, and we will read the value for the counter. So let's have the message like thread dot current thread dot get name and reads counter. So this should be for the get value method, and for the read write lock demo we will create another class. So let's call this class as read write lock demo, and we would have a main method. Inside the main method we create the object for the shared resource, and we will create a couple of reader threads. So let's do that. So for I, and inside the loop what I do is I create the reader thread, so new thread, and for int j as 0, j less than 3, j plus plus, resource dot get value. And now let's assign a name to this thread. So let's call this as reader thread and pass the value as I plus 1. Now we will start this thread. So let's call dot start on this one. For the writer thread let's create one. So thread writer thread new thread, and we do this for 5 elements. So share resource dot increment, and likewise we will provide a name to the writer thread. So let's call this as writer thread, and let's start this thread. So let's run this code and see how is the outcome like. Alright, so what we see is that we have reader thread and there is another reader thread, the two that we have created, right? And they are reading a value of 0 initially because the writer thread has not been executed yet, the value remains to be 0, the initial value. Then we have the writer thread, and what the writer thread is doing is it's going to increment the value 5 times. And as a result, what we say is the value gets incremented to 5. Now we have the reader thread, and the reader thread reads the value, and the value that it's reading is 5. Again, the reader thread is invoked and it's reading the value as 5. So this is how you could make use of the read-write lock if you have such a use case wherein you want to bifurcate the lock acquisition for readers and writers separately. So that should be it for the code demonstration. Let's complete this section of read-write lock by learning about the behavior of wait queue in the read-write lock. So let's visualize how the wait queues are arranged and managed in the case of a read-write lock. In the case of a read-write lock, there would be two types of threads in the wait queue. One type of threads are those which want to read the data, and the other type is which want to write the data. Let's say that initially there is one writer thread and two reader threads. In this case, the reader threads will be allowed to acquire the read lock. This is done because it's efficient. Essentially, what you are allowing is two threads to be executed as compared to the one. Once all these reader threads are done with their operation, the writer thread waiting in the same queue is allowed to acquire the write lock. What happens in the scenarios when there is a writer thread waiting in the queue and the reader threads keep on coming to the queue? Should they all be allowed because it's faster to execute? Well, if we do so, the writer threads will be starved, and this is not good. So this kind of low-level optimization is taken care of depending on the type of implementation you choose for the read-write lock. For example, Reentrant read-write lock is one such implementation. The key takeaway here is that read-write locks are optimized for reading and writing operations in the most efficient manner possible. And you as a developer should be good to make use of this lock without much optimization or configuration concerns. So whenever you have such requirement, consider making use of this lock. Let's learn about this very important concept of visibility problem. Before we start learning about the visibility problem, let's take an important detour to understand and visualize how cores, registers, and caches are placed along with the RAM. The image here is showing a machine which has 6 cores. On the first layer, we have the cores. Cores are the piece of hardware which are responsible for all the compute activity. Loosely speaking, core itself does not have any storage capability. It can only compute. But in order for the computation to happen, we need to have some sort of data storage as well, right? This is where we have different type of storage units. Let's know about them in a very brief manner. First on the list is a register. Every core has a dedicated storage component which holds the data temporarily during the execution of the instructions. This storage component is known as register. It has the least amount of storage capacity. Each core has a dedicated register. The next one in the line is the component of L1 cache. L1 cache is a small but a very fast memory. It plays a crucial role in improving the performance of the CPU by reducing the data access time to and from the main memory, which is also known as the RAM. Each core has a dedicated L1 cache. The next component is the L2 cache. It is a larger capacity cache as compared to the L1 cache. Its role is to complement the smaller and faster L1 cache. It does so by providing additional storage for frequently accessed data and instructions. L2 cache is integrated in two ways depending on the architecture of the processor. In one approach, the L2 cache is shared across different cores, whereas in the other approach, we could have dedicated L2 cache for a core. The presentation that we have here, we are showing a shared L2 cache, where the cache is being shared by two cores. For example, here core 1 and core 2 are sharing this L2 cache. Likewise, core 3 and core 4 are sharing this particular L2 cache, and so forth. The third type of the cache is L3 cache. It sits between the L2 cache and the RAM, which is also known as the main memory. Its role is to provide a larger pool of cached data and instructions which can be shared among multiple CPU cores. The final type of a storage layer is RAM, and as told earlier that this is also known as the main memory. It serves as a temporary storage for data and instructions that are actively being used by the CPU. So on the one end of the spectrum, registers store the data specific to a core, and on the other end of the spectrum, we have RAM, which stores data and instructions being worked upon by all the cores of the CPU. When we go farther from the core towards the RAM, the latency and memory size increases. So RAM would be of larger size as compared to L3 cache. L3 cache would be of larger size as compared to L2 cache, and likewise register is the one which has the least amount of storage capacity. But since register is closer to the core as compared to the L1 cache and L2 cache, register would be faster, in fact the fastest type of memory, whereas RAM is the most farthest one from the core, so it is the slowest of the lot. So the RAM would be the slowest memory and the register would be the fastest memory. Let's see this diagram. What we have here is a code snippet, and basically we have two methods. Assume this write method is being used by a writer thread and this read method is being used by a reader thread. And this particular code snippet is being executed in this kind of a machine, wherein we have two cores, and core 1 is executing thread 1 and core 2 is executing thread 2. So to begin with, there is a variable whose value is 0. The count variable starts with value 0, and assume at certain point of time thread 1 gets to execute on core 1 and thread 2 gets to execute on core 2. So basically both of these two threads are running in parallel. So the value of count is updated as 1 by the writer thread, and at the same time the value count is loaded in the value. So what would happen if you try to access the value of val by either printing it or debugging it? So you may see something like this. So to begin with, count is 0, that is in the shared cache. Then the count is updated to value 1, and this value is there in the register which is local to core 1. Now core 2 is running thread 2 and it is trying to access the value for count. So remember that as of now the value of count is 1 is only with this register. It has not percolated to the shared cache level. So the value that is present for this count variable is still 0. So the value that is assigned to val is still 0 in this register. And when we try to print this value, we will get the value as 0 as opposed to what we were expecting, which should have been 1. So this is not something which is expected and correct, right? So this kind of behavior is called as the visibility problem. Java provides a solution for this with a keyword called as volatile. Using this keyword ensures two things. First is, whenever there is a change in the value, it's flushed to the shared memory. Second is, whenever there is a value which is supposed to be read, it's read from the shared memory. The shared memory is usually, and in most of the cases, L3 cache, which we saw earlier to be the shared cache, and this one is a level up to the RAM. So basically what I'm trying to say is, let's say if I used volatile with this variable, so what I'll do is I will write this as volatile keyword then int count, right? And then when thread 1 is executed and any value to this variable is changed, it won't be only there with the register, rather it will be written to the shared cache as well. And since this variable has been made volatile, the thread won't read this value from the register or any other cache, rather it will directly read from the shared cache. So on the write, we are ensuring that the value for the particular variable which has been made volatile is going to the shared cache, and for the read as well, we are ensuring that value is read from the shared cache itself. So that would avoid us in reading wrong value. And this is how the volatile keyword helps us with the visibility problem. There is a word of caution we should always follow while making use of the volatile keyword, however. While volatile does help with the visibility problem, as a side effect, It slows down the code and thus the application. It's a no-brainer that with the uses of volatile, the many layers of caching are removed, and so are the latency optimization benefits which we gain when we use the caching. So when not needed, the uses of volatile keyword should be strictly avoided. Deadlock is an important concept we should know about when we are writing multi-threaded code in Java. Let's learn about the same. What is a deadlock? Here is an image which tells us about a deadlock situation. Let's have a closer look. Here we have two threads which are running. Thread 1 at some point of time is going to need lock A, which is represented by a green color. Then after some point in time, thread 1 is going to need lock B, which is represented as blue color. Now let's look at thread 2. This thread is going to need lock B at some point of time, and then it's going to need lock A after some time. Please note that in both the threads, both the locks are needed to be acquired in order for the processing to get completed. Only after the processing has been completed, both the locks A and B will be released. Let's imagine this scenario at time t. Thread 1 needs lock B while it has already acquired the lock A. Likewise, thread 2 needs lock A while it has already acquired the lock B. But both the threads won't be able to acquire the needed lock because their need is being held by the other thread, and neither of the threads are in a situation to let go of their acquired lock since it's needed to complete the processing of the thread. So in this situation, none of the threads could proceed with their execution, and this situation is called as a deadlock. So here is a formal definition of the deadlock. In a multi-threaded context, a deadlock occurs when two or more threads are blocked forever, each waiting for the other thread to release a resource they need to proceed. This situation creates a cycle of dependencies with no thread able to continue with its execution. So how can we spot deadlocks in our code? There could be two approaches. One is the manual approach, other is the programmatic approach. So let's learn about the same. Well, detecting or spotting locks at the compile time is not an easy task. This is so due to multiple reasons. Java comes with multiple types of locks, so multi-threaded code can be littered with different types of explicit and implicit locks. Also, there could be multiple sources of threads in the codebase. Due to these two factors, combined with the fact that the thread execution and CPU allocation is not deterministic, it's nearly impossible to figure out when which lock is going to be acquired by which thread. Moreover, the example we saw earlier was a simplified version where we had two threads and two locks. However, in real world, it won't be this simple. There is a good amount of possibility to have multiple threads and multiple locks which could lead to a deadlock situation. And thanks to all of these complexities, it's nearly impossible to detect a deadlock by just looking at the code. So the manual approach is something which is not very efficient, neither it's the suggested approach. So how do we detect the deadlock in code? Let's have a look on the programmatic approach of detecting the deadlock. So now that we have learned that detecting a deadlock is very difficult in manual way, are there any other tools which can help us in this detection? Good news is, yes, there are tools and ways in which we can detect deadlocks in our code. Two of the most common approaches are taking the thread dump and uses of the thread mxbean to programmatically detect cyclic thread dependencies, which can lead to a deadlock. So let's have a brief code demonstration where we will be knowingly introducing deadlocks in our code and then use these methods to detect the deadlock situation. So in order to demonstrate the deadlock code, I'll create this package and let's call this package as other concepts, and let me create this class as deadlock demo. We will have two locks, so lock A and make this as a reentrant lock. Let's duplicate it, create another lock B, and we will have two methods. First would be a worker1 method, other would be worker2 method, and let's implement these. So public void worker1. It will start by acquiring the lock A, and then there would be some message which will be printed like worker1 acquired lock A. Next we will introduce some sort of sleep time. So let's call thread.sleep for 200 milliseconds. Let's handle the interrupted exception. Let's throw it as a runtime exception. And then we acquire lock B. Then let's print some message. It could be something like worker1 acquired lock B. And then we start by unlocking the locks, which is lock A.unlock and lock B.unlock. So this should complete the first method, which is worker1. Now we will duplicate this and we will write the worker2 method implementation. What worker2 does is it starts by acquiring the lock B, and then we will of course change the messaging here, and again we have a sleep for 200 milliseconds. And now after lock B is acquired, lock A will be acquired, and again we will adjust the messaging, and then we can have lock A unlock itself and lock B unlock itself. Now let's write the main method where we will be creating the threads and executing these things. So we start by creating the object for the class so that we can invoke the methods. Now what we can do is we can say new thread demo dot worker1. We will give this thing a name, this thread a name, and we call dot start. Likewise we'll create a thread which will be making use of the worker2, and we will adjust the name here for the thread which will be worker2. So let's run this thing and see what is the output like. Alright, so what we see is worker1 has acquired lock A and worker1 acquired lock B. So essentially the worker1 got a chance to run, and after that point of time worker2 was supposed to be run, but now we are in a deadlock situation because worker1 has acquired the lock B, and here worker2 requires lock B in order to do its processing. But since the worker1 has acquired lock B and not released it yet, the worker2 cannot get hold of it, and that is the reason we have entered into a situation of deadlock. What we can do about it now? Well, in such cases you cannot do anything, but your code will be sort of in a deadlock situation and you will have to terminate it. So as told earlier that we can either take a thread dump, or maybe we could use the other approach of using the thread mxbean to understand what part of the code is leading to this deadlock situation, right? So let's understand the first approach, which is using the thread dump. So what we will do is we will go to the terminal. So let me come out of the distraction free mode, and here we go to the terminal, and in the terminal we will list all the processes which are running Java. So we see that these are the processes, and the one which we are concerned about is this deadlock demo, and here is the process ID. So what we do is we call kill -3 and we pass the process ID, which is this one. Hit enter and go back to the output console. So here we can see that we have lots of messages which are getting printed. So this is something that we had earlier, right, where we had the deadlock situation. Now we are seeing something called as a thread dump, which is the full thread dump, and it's going to show certain information regarding the thread classes, certain messages, and so on and so forth. Of course, you could try to do it yourself on your system and read through all these things, what exactly is being told. But the most important thing is in the last. So scroll to the last, and here we have this message, and this thing says that found one Java level deadlock. What does it say? It says waiting for ownable synchronizer, a fancy name for the lock, which is held by worker 2. So worker 1 is saying that it's waiting for a lock which is being held by worker 2, and the worker 2 says it's waiting for a lock which is held by a worker 1, right? So what you could do is you can scroll further down and you could see that this is one line which is being hinted in your code. Click it out and you could see that this is a probable reason. So in your use case, in your real world use case, whenever you are faced with this kind of situation, this is the way in which you could find out the process ID and kill it with -3 as the argument, and this will help you out with this thread dump, and you could figure out, at least you have a point of investigation where you could try to understand what is the deadlock situation and what part of the code is leading to this scenario. So this is the approach in which you could analyze the thread dump to understand the deadlock. There is another approach, however. So let's go to the code, and we will have to modify something in our code in order to understand that particular approach. So what we are going to do is we are going to make use of this thing called as thread_mx_bean, and we will create another thread, let's say a thread 3, which is going to execute forever, and it will be done after an interval of every 5 seconds. So the idea is to probe the code and to understand if there are any threads which are in deadlock. So let's write the code. It will be much simpler to understand that way. So let's start by creating a thread, and let's supply the code for the same. So the first thing is we have thread_mx_bean. Let's call this as mx_bean, and it provides a management factory using which you could create the thread_mx_bean, and while true, what we can do is we can say mx_bean find me all the deadlock threads. It will return a array of long, which are basically the thread IDs, and if the thread IDs does not happen to be a null, so we can print this message that deadlock detected, and we can iterate over the long thread ID for each of the thread IDs in the thread IDs, and then print this message: the thread with ID, thread ID is in deadlock. And once we have printed this message, what we need to do is break out of the infinite loop, and if that is not the case, so we need to do this every 5 seconds. So let's put a timer of 5000 milliseconds and catch the interrupted exception, and we will throw it as a runtime exception. And finally, let's call the dot start on this thread. So here is what is happening. We have created a thread which is going to run every 5 seconds, and we are making use of the management factory to get an object of the mx bean, and the mx bean has a method which will give me the deadlock thread IDs if there are any threads which are in deadlock, and I am simply going to iterate over the given thread ID, right, and print the message here. You may be wondering that thread ID is fine, but what if I need certain extra information? How can I do that? Well, there is another method in the thread mx bean which is called as get thread info. So let's make use of that as well. So we can say mx bean get thread info, and it's going to accept a long array which is the thread IDs, and what it returns is an object of thread info array, and let's call this as thread info. So thread info contains a lots of information, as in what is the thread name, what is the lock name, where exactly it is waiting for which lock, and all those things. So in this example we don't really need to showcase all those things. So but the idea here is that if needed, you could certainly make use of this particular line and iterate over the thread info and get the required information. So let's run this and see the output. So run, and initially we have executed these threads. There is a timer of 2 seconds, remember, 2 milliseconds rather, and then after some point of time this thread kicks in and it's going to say thread lock detected, and thread with ID 21 is in deadlock and thread with ID 22 is in deadlock. And as I told earlier that if you need certain more information, you could make use of the thread info object or the class, and these are the information it contains, and you could make use of this information in your code as per your need. So now that we have seen the code demonstration for the deadlock, let's understand how can we prevent deadlocks. So are there any approaches or suggestive measures using which you could get rid of the deadlocks, or at least try to write a deadlock free code? So the first and foremost is use timeouts. So let's say when your thread is trying to acquire a lock, giving a timeout will ensure so it's not going to end up into a situation where it's trying to acquire a lock for infinite time, right? And thus it will help in avoiding the deadlock situation. So uses of timeouts is a good approach in order to avoid deadlocks. The second thing is the global ordering of the locks. So another thing we can do is to pay attention to the global ordering of the locks. What it means is, let's say we have 2 threads and 2 locks to acquire, for example lock A and lock B. Both the threads should first acquire lock A followed by lock B. So in that sense it won't be a cyclic dependency scenario and it will avoid the deadlock situation. The third thing is to avoid any sort of nested locking. So whenever feasible, we should always avoid locking within already locked section. And the fourth preventive measure is to make use of the thread safe alternatives. So whenever feasible to do so, use thread safe collections and atomic variables and minimize the uses of locks. Sure, the thread safe collections do make use of the locks under the hood. However, in general, the code implementation of the standard thread safe are battle tested industry solutions. So there is a little to no chance of running into the deadlock situation. So this should be it for the concept of deadlock, and these are the certain measures using which you could try to avoid deadlock situation. And even if you are in one situation of a deadlock, what are the different approaches using which you could analyze your code to correct it. Atomic variables are an important tool which help us in writing concurrent code in Java. Let's learn about the same. So what's read, modify, write cycle? In order to understand what is a read modify write cycle, let's have a quick look on this image. There are two threads and a variable called as count which has the value as 0. There is a processing part which needs to be done on this value, which is to simply increment the value by the count 1. Two threads get to execute this process of incrementing the value. Imagine if these two threads are going to be executed 1000 times. What we would expect is that the final value of the count should be 2000. However, this is not the case. So 1000 times the value will be incremented by thread 1 and another 1000 times the value should be incremented by thread 2. Effective value expected is 2000. But when you try to run this code, you will find the value would be less than 2000. Moreover, it will be very much inconsistent. So at some times you could get some different value and at the other time the value would be totally different. So there is some sort of inconsistency. Let's learn why so. Well, the reason lies in the fact that how do we actually understand the increment operation and how it is actually performed on the low level. So on a very low level, there are 3 steps which are performed when we increment the value of a variable. As part of the step 1, the value of the variable is loaded in the register. Remember, register is the local storage which is the nearest and almost native to the processor core. As the second step, this value is operated on, as part of which it gets incremented by 1. And finally, as the third step, the incremented value, the new value, is assigned back to the variable count. So to understand with an example, at step 1 the value is 0 which is loaded in the register, and at a step 2 it becomes 1, and finally at the step 3 the value 1 which has been incremented from 0 to 1 is assigned back to the counter. This entire flow is called as the read modify write cycle, and this is the core reason behind the inconsistency in the value if it's incremented across multiple threads. Since I have already covered this concept in more depth with examples, I won't go into much details. However, if you could remember from the previous discussion, what's exactly happening is that the entire process of incrementing the value count ++ is divided into 3 steps, and let's say if thread 1 is operating on the count operation which is involving these 3 steps, and at the same time somewhere between these steps if thread 2 is going to interrupt, then this problem will occur, and this is the sole reason behind the inconsistency. So now let's talk how can we solve this without using any kind of explicit synchronization mechanism. So what are atomic variables? What we saw earlier is something called as a non-atomic operation. What it means is essentially an operation, for example incrementing a value, can be broken down into 3 steps. Thus it's not atomic, something which can be broken down. So what atomic variables in Java do is that there are a type of variable that support lock-free thread-safe operations on single variables. They ensure that any kind of read modify write operation such as incrementing or updating a value are performed atomically. It prevents race conditions, and this makes them crucial in concurrent programming as they help in maintaining the data consistency and integrity without the overhead of traditional synchronization mechanisms. Atomic variables provide built-in methods that perform atomic operations. It ensures that actions like incrementing and updating are completed as a single and non-divisible step. This eliminates the need for synchronized locks, which can be costly due to locking overhead and potential thread contention. As a result, atomic variables offer a more efficient way to achieve thread safety in the concurrent programming. There are different types of atomic variables. The atomic variables in Java are basically classes. Each of these classes are used for a particular data type, for example integer, long, etc. The java.util.concurrent.atomic package contains all such atomic variables. However, atomic integer, atomic boolean, atomic long, etc. are some of the important and the most commonly used ones. So if you wish, you could go to the concurrent atomic package and explore the other atomic variable options that we have. Now with that in mind, let's understand a few of the basic operations that we can perform on these atomic variables. These atomic variables provide quite a few operations which we can make use of as per our need. However, there are a few which are very commonly used. Let's learn about those. The first one is get. So it fetches the current value. Next one on the list is set operation, and as the name suggests, it will set some value. The third one is compare and set, and this operation expects two values which are expected and update. It sets the value to the update value if the current value is equal to the expected value. Then we have these two operations which are equivalent to the pre and post increment. This operation atomically increments the value by 1 and returns either the new value or the old value. The fifth one and the final operation on our list is get and decrement and get, which are equivalent to the pre and post decrement. This operation atomically decrements the value by 1 and returns either the new or the old value. Please note that these are the most commonly used operations, and there are much more depending on the kind of atomic variable you are planning to use. You could explore the respective classes to find about their supported operations in more details. But having said that, these are a few of the commonly seen operations that you would come across when you write the code related to atomic variables. Now let's conclude the discussion on the atomic variables by going through a code demonstration, and we will be using the atomic integer as the one of the atomic variables to showcase the uses of atomic variables. So in the other concepts package, let's create a class. Let's call this as atomic variable. And what we are planning to implement is some code which is going to work on a counter variable, and there would be a couple of threads working on this, and we will see how we could make use of the atomic integer to help us with the inconsistencies of multi-threaded programming. So let's start with having the count variable. So the initial value is going to be 0, and then we will have the main method. So we will first create the thread 1. Let's call this as thread 1, and what this will do is it will run for, it will call count plus plus for 1000 times. Let's have the similar thread. Let's call this as thread 2, and it will also do the same. That is, it is going to increment the value by 10,000 times. So let's start these two threads. Let's remove the 1 and type it as 2. We will have to wait for these threads to be completed. So let's do that. Surround with try catch. Let's put 2 here. And now let's print the count value. So count value is count. So let's execute this code and see what is the output like. Alright, what we are seeing is the value is 14,103, which is not correct, of course, because what we wanted is that we have 2 threads which are going to increment the value 10,000 times. So effectively the value should be 20,000 when we print it here, but that is not the case. So the reason this is happening is because we are using count plus plus in a multi-threaded context, and which is of course not an atomic operation, and due to the reason that we learned in the theory section, this is the problem we are facing. So how can we correct this? So let's make use of the atomic integer. So private static final atomic integer, let's call this as counter, and let's create the atomic integer. Initial value is going to be 0. So instead of having this count plus plus, let me comment it out, and what we can have is counter dot increment and get. So what this increment and get does is it is going to increment the value of the counter, which is 0 to begin with, and it will get the value. So essentially, if you want, you could capture it somewhere, But even if you don't capture it, the counter object is going to hold the updated value. So let's say if it's getting executed for the very first time and the initial value is 0, then the value for counter will become as 1 because it's going to increment it and get the value which is self-assigned. If you want, you could capture it as some variable as I showed earlier. Now for the second thread, let's comment it out as well. And again, here we could call increment and get on the counter. So that is about the uses of counter, the atomic integer in the thread section. Now everything else remains the same, and here we will try to print the value of counter instead of count. So let's print it out and let's run this and see the output. So here is the output. What we see is the value is 20,000. Let's run it a couple of times to see if it's working consistently. So yes, we are getting the same value over and over again. What it means is the value is consistent, and the problem that we were facing earlier of inconsistency because we're using a non-atomic operation, that was the count plus plus, that problem has been fixed when we started using the atomic integer. So as I told you earlier, that atomic integer is part of the Java util concurrent atomic package, and likewise we have many other options. So if you go to this package, you will see that we have atomic, and we have atomic boolean, atomic integer, atomic array, and so on and so forth. There are lots of options that we have in the atomic package. So you could explore all of these things depending on your need. But having said that, this should conclude the discussion on the uses of atomic variables. Semaphores are an important concept whenever we talk about multithreading in Java. So let's learn about the same. What are semaphores? A semaphore is a synchronization mechanism used to control access to a shared resource in concurrent programming. It uses counters to manage the number of allowed accesses to the resources, preventing race conditions and ensuring safe concurrent operations. Semaphores can be binary or counting. It depends on the number of permitted access. While I was learning this concept, the terminology of semaphore used to confuse me a lot. The word semaphore is not very intuitive, and it does not reflect something which is common in our day-to-day uses. So why do we name a particular concept as semaphore? If you are in the similar situation, let's learn what does this word mean. The term semaphore comes from the signaling devices used in railway and maritime contexts to control traffic. In programming, it similarly signals and controls access to shared resources among concurrent processes. Essentially, this term semaphore is not commonly used in everyday language among native English speakers. It is primarily known in a specialized context like programming, operating systems, and historical references to signal devices in transportation. So, with having known the definition of the topic, let's understand how is this semaphore used with some visualization. Imagine we are building an application which needs to connect to a third-party service. So this is our application and this is the third-party service. So this is the application and this is the third-party service. Due to some constraints, the third-party service could be accessed only by a limited number of threads at a given point of a time. So for example, what it means is only 3 concurrent calls would be allowed to this third-party service from our application. So in order to implement such scenario, we need to ensure that we have some sort of restriction in place. In such situations, we can think of making use of the semaphore to implement such restrictions. For example, assume that our application has 50 threads in threadful. However, the third-party service is going to allow only 3 threads. So in that case, we can think of using the semaphore. Now let's understand the concept of semaphore with this image. Let's start with an assumption that semaphore at the core of it is nothing but a permit mechanism. The image shown has 3 boxes. These three boxes are nothing but permits. So at the moment, this semaphore is going to allow 3 threads to be run. So essentially, if there is a thread that wants to execute, it will ask the semaphore that, hey, I want to be executed. So in that case, semaphore will check that does it have any permit or not. So if there is a permit, that permit will be given to a thread. So basically this permit is like a token, and once a thread acquires it, then it's going to do its processing. So this is what we mean when we say that at this moment this semaphore is going to allow 3 threads to be run. To begin with, we have thread 1 which wants to execute. So it calls acquire on the semaphore. The acquire method is like it's requesting for a permit. Now that at the given instant we have 3 permits available, the thread 1 is going to be allowed and it will execute and access the third party service. So essentially thread 1 comes and it says, hey, I want 1 permit to be executed. Semaphore is like, alright, I have 3 permits, here you take this one and you can proceed. So once it's given, you could imagine that this permit is no more. So essentially you have 2 permits left. And once this permit is assigned to thread 1, it goes ahead with its execution. So thread 1 is essentially allowed to execute. So once thread 1 has been given the permit, semaphore will have 2 available permits. And while thread 1 is executing and accessing the service, let's say we have another threads which are thread 2 and thread 3 which come to semaphore asking for permits. And at this moment, the semaphore has 2 permits available. So it will give the permits to thread 2 and thread 3. And essentially after these permits are given to thread 2 and thread 3, they also go about with their execution. So thread 1 starts with its execution and so does thread 2 and thread 3 after acquiring the permit. Now let's imagine at some point of time in future, thread 4 comes into picture and it's going to the semaphore and say, hey semaphore, I want to execute, and in that to happen, I want to acquire the permit from you. So at this moment, semaphore is like, alright, that's fine that you want to get executed, but I don't have a permit with me as of now. So what you can do is, you could wait, and due to this, thread 4 gets blocked. So thread 4 had called the acquire method and it's going to get blocked on the acquire method. And sometime in future, when thread 1 is done with its execution, it will say, alright, I am done with my execution. Now I am going to release the permit that I had acquired. So the permit will be given back to the semaphore. And as soon as that permit is given back to the semaphore, the thread which was waiting for a permit in the semaphore will acquire it and proceed with its execution. So let me revert back the image, and now we have all the 3 permits available with the semaphore. So at some point of time, thread 4 got a chance to execute by acquiring the permit. So this is the way in which semaphore works. So let's understand what exactly is this release method. Well, thread says, hey semaphore, I am done with my execution, thus I'm returning back your token, your permit that you gave me earlier, and you could make use of it as per your wish. So you could understand that semaphore permits are nothing but kind of reusable tokens in that sense. So if you notice, at any given point of time in this semaphore, we can only have 3 threads executing at maximum. And that is what semaphore is used for. So essentially what we have done is we have restricted the count of threads which are going to access the third party service using a semaphore. Now that we have understood how exactly semaphore is working under the hood, let's have some quick code demonstration which will showcase us how we can make use of the semaphore in our code. So here I am in the IDE. I will create a new class for the demonstration. But before I create the class, let me tell you briefly what exactly I'm planning to build. So I'm planning to build a small use case where we will be making use of some third-party service to scrape the data. Don't worry, it's not going to be something difficult. It's rather just a dummy kind of method the entire idea is to showcase how we can use the semaphore rather focusing on the scraping part of it. So let's get started, and I will create a class. I'll call this as a scraper, and let's have this main method to begin with, and I will create the scrape service, which is the service which will be called by the scraper class. So just as a good practice, I am going to make the scrape service as a singleton class. Not that it's needed for this demonstration, but just as a good practice, let's have it as a singleton, and let's have this instance. And what we will be needing is a semaphore. So let's initialize the semaphore. It provides a constructor wherein we can pass some value. So this semaphore is going to have 3 permits, and we have a method that is called scrape. What this scrape is going to do is it's going to run in a try catch block. Let's have this interrupted exception, and this will throw a new runtime exception, and we will also have a finally. Why? We will look at it in some time. So to begin with, this thing is going to acquire the semaphore. So it will call the .acquire method on the semaphore, and then we have a helper method which is something like invoke scrape bot. So invoke a scrape bot is the actual third-party service invocation, wherein we are going to call the third-party service and do the scraping task. So we will implement this method in some time, but for now let's have this signature here. And imagine that some thread has acquired the semaphore permit and it got terminated due to some reason, or maybe it went into a deadlock situation. So what happens is the semaphore permit is acquired forever, but we don't want that to happen, right? What we want essentially is that once a thread is done with its execution, it should be releasing it. So similar to the way in which we used to acquire and unlock the locks, right? We will be using the try and finally block, and in the finally block we will say semaphore dot release. Idea is that in either case of success or failure, the execution inside the finally block will take place, and that is when we are going to release the semaphore. So let's implement the invoke scrape bot method. So it's private void invoke scrape bot, and this is nothing. This is just going to print some message. So let's have the message as scraping data, and to mimic some sort of execution time, we will have some sleep introduced in the code. Let's say this is for 2 seconds, and since we have given thread.sleep, we need to handle the exception of interruption, and the way we will do this is we will throw a runtime exception with the exception. Not the best way to do it. This should do for the demonstration purposes. So now let's go to the main method and try to make use of this. So what I'll be doing is I'll be creating a new cached thread pool, and using that cached thread pool I'll be submitting the tasks for the scrape service. So let's do that. So I'll be making use of the try with resources pattern. So executor service and executors dot new cached thread pool, and let's say I want to do this for 15 times, and service dot execute new runnable, and this will call the scrape service scrape. So what we have done is we are creating this service, that is the new cached thread pool, and we are supplying this runnable. We are calling this script service method inside this runnable 15 times. So what we would expect is that at any given point of time, only 3 threads are executing. So let's run this and see the output. So here is the output. We have a scraping data, then we have a scraping data, then we have a scraping data, finally we have a scraping data. So what is happening essentially is, out of all the 15 times we have submitted the runnable, we are just allowing 3 threads to execute simultaneously. So scraping data is printed thrice, scraping data is printed thrice, and so on and so forth. So this is kind of demonstrating that using a semaphore, we are restricting how many threads can run at a given point of time. Please note that how many threads will be actually running at a given point of time will also depend on how many cores you have and all those things. But the whole idea is that if you use a semaphore and some sort of permit, then in the worst case possible, at max, only those many threads will be running at a given point of time. And that is the whole intention and idea behind using the semaphore. So now that we have seen the code demonstration, let's learn a few more things about the semaphores. We also have a concept of multiple permits. Please note that we can acquire multiple permits at a time. For this, we have an overloaded method of acquire which allows us to enter the number of permits we want. So when we call semaphore.acquire, you can pass a value. So let's say semaphore.acquire and you pass a value of 2. So 2 permits out of 3 will be taken by the thread. However, we should always ensure that the number of permits we take should be equal to the number of permits we are returning back by calling the release. So like we had passed the number of permits in the acquire method, we also need to pass the number of permits in the release method as well. So if .acquire is 2, .release should also be 2. And there are some other methods in semaphore as well. Let's learn about those. The first one is try acquire. So when this method is used, the thread will try to acquire the permit. If there is no permit available, the thread won't be blocked. Rather, it can do something else. Then we have try acquire with timeout, which is essentially the same as try acquire, except it accepts some sort of timeout. The next one is the available permits, and as the name suggests, the available permits returns the number of available permits with a given semaphore. The final one on our list is this new semaphore, which accepts count and fairness. Well, this is an overloaded constructor of the semaphore. It accepts a fairness criteria, which is a Boolean value, and when given as true, the thread waiting the longest gets the chance to acquire the permit once it's available with the semaphore. So that's all about the semaphore. It's very easy and intuitive to understand. Essentially, it's a mechanism to introduce a controlled bottleneck situation to ensure that there is an upper limit on how many threads can work on a shared resource at a given point of a time. Let's learn about the mutex. So what is a mutex? Mutex is a short form of the word mutual exclusion. It is a synchronization mechanism used to control access to a shared resource in a multi-threaded environment in Java. The primary purpose of a mutex is to ensure that only one thread can access a critical section or shared resource at any given time. It prevents race conditions and ensures data consistency. Wait a second, hold on. Are you thinking that it sounds very similar to some other concepts we learned earlier related to multithreading? Well, you are very correct if you are thinking so. Mutex is nothing but a fancy term for locks and synchronized blocks. Moreover, the concept of mutex encompasses any mechanism that ensures any sort of mutual exclusion. It means only one thread can access a critical section at a time. In Java, this concept is realized through synchronized blocks and lock interface. You may have another doubt. You may be thinking, if the mutex is indeed just a fancy term for locks and synchronization, why do we have this concept at all? Well, the reason is somewhat historical in nature. The term mutex is a fundamental concept in computer science and concurrent programming, which predates the specific implementations found in languages like Java. The concept of a mutex is used widely in both theoretical and practical contexts to describe a mechanism which ensures mutual exclusion and thereby preventing multiple threads from accessing a shared resource simultaneously. So effectively, mutex is the term for general concept of mutual exclusion in context of multi-threaded environment, and the approaches like using of locks and synchronized blocks etc. are tools which help us in achieving this requirement of mutual exclusion. So if you understand any of the concepts like lock, synchronization etc. which provide mutual exclusion of a shared resource, you very well understand mutex. So that's all about mutex. There is nothing new to learn here as such because we have already covered the concepts related to locks and synchronized blocks in Java. Fork join framework is another important concept in Java. Let's learn about the same. The fork join framework is a concurrency framework which was introduced in Java 7 to simplify the process of parallel programming. It is designed to take advantage of multi-core processors by dividing tasks into smaller subtasks, executing them in parallel and then combining their results together. The fork join is very similar to Executor service, which we learnt about earlier. In the interest of refreshing your memory, Executor service mainly consists of some sort of data structure which stores the task to be executed, and there is a pool of threads which pick the tasks from this data structure and work on the task. Depending on the use case, you could just execute a task and not return anything, or you could return a value from the execution of the task. So in these two aspects, the fork join framework is exactly the same as the Executor service. However, there are certain dissimilarities between the Executor service and fork join framework. The fork join is different from the Executor service in the aspects of subtask creation, and the fork join framework can create subtasks, which is not the case with the Executor service. Now let's learn about the differences between the fork join framework and the Executor service. The fork join framework differs from the Executor service in two aspects. The first one is the task producing subtask, and the second one is per thread queuing and work stealing. In the case of fork join framework, a task is capable of creating subtasks to simplify the problem being solved. Consider this as the standard divide and conquer approach, which is not the case with the Executor service. Unlike the Executor service, where there is a shared task queue, the threads in the fork join framework have their dedicated task queue. There is also this mechanism of load balancing where a thread could pick tasks from the other queue. This approach is called as work stealing. Now it's time to learn why do we have fork join framework. You may be wondering, why do we have yet another framework on top of all the things that we have learnt so far in the multithreading? Well, fork join framework is not there without any reasons. Below are a few reasons why the fork join framework was provided as part of the Java. The first one is the utilization of multi-core processors. Modern processors have multiple cores, and traditional single-threaded or poorly managed multi-threaded applications do not fully utilize the computational power of these processors. The fork join mechanism efficiently manages multiple threads to leverage all the available CPU cores. The next one is simplified parallelism. Writing parallel code manually is a complex and error-prone activity. The fork join mechanism abstracts out much of this complexity, and it makes it easier to develop parallel applications. Finally, on the list of why do we need fork join framework, we have this concept of efficient work stealing algorithm. The framework uses a work stealing algorithm where idle worker threads steal tasks from the busy threads. This ensures that all the threads remain productive and improve the overall performance. So, as I told earlier that we have queues on per thread basis, and let's say a thread is done with its execution of the tasks in its queue, so in that case that thread could steal work from the other threads from the other queue where it has some other tasks aligned to be executed. It's very equivalent to the mechanism of load balancing. So you see, the fork join framework has a certain pattern to it, and due to this, we have certain use cases which fit very well with the uses of this framework. For example, sorting a large data set, performing operations on large matrices, processing large collections of data in a parallel fashion, and so on and so forth. Now it's time to learn about the key concepts in the fork join framework. Forking in the fork join framework is the process of breaking down large tasks into smaller independent subtasks which can be executed concurrently. This is achieved using the fork method provided by the ForkJoin task class. The next concept is that of joining. What it refers to is the process of waiting for the completion of a fork task and combining its results. This is done using the join method. Then we have the recursive task. The recursive task is an abstract class and it is used for the task which return a result. It is parameterized, which means that the type is the type of the result which is produced and returned by the task. So whenever there is a need to compute a result and return it after completing the task, the recursive task class should be used. Loosely speaking, you could imagine this to be parallel to the callable interface. Then on the list, we have recursive action. It is used for tasks which don't return any result. It does not accept any types. When the task performs an operation which does not need to return a value or a result, we should use recursive action. And loosely speaking, you could imagine this to be parallel to a runnable interface. So what is a ForkJoinPool? Let's learn about the ForkJoinPool, and I promise that this is going to be the last theoretical topic in this section before we move to the more juicy implementational side of ForkJoin framework. Well, ForkJoinPool in Java is a specialized implementation of the Executor service interface, and it is designed so to support the ForkJoin framework. It is optimized for parallel processing and efficient management of tasks, which can be broken down into smaller subtasks. Below are some key concepts and aspects which are related to the ForkJoinPool. We have this concept of work stealing algorithm. So ForkJoinPool uses a work stealing algorithm to efficiently manage and balance the workload among threads. When a thread finishes its task, it can steal tasks from the work queues of the other threads, ensuring that all threads remain productive, and it reduces the idle time as well. Next, we have parallelism. So the pool can automatically determine the level of parallelism based on the number of available processors. You can also specify the level of parallelism when creating the ForkJoinPool instance. So we have two operations like fork and join. So the tasks submitted to the ForkJoinPool can be split into smaller subtasks and their results can be combined together. This mechanism supports the divide and conquer approach for solving the complex problems. Finally, the ForkJoinPool is designed to manage the instances of the ForkJoin task and its subclasses, which are recursive task and recursive action. So these tasks encapsulate the logic for splitting the work and combining the results. So in a nutshell, to summarize the theoretical section, what we have is a ForkJoin framework and ForkJoinPool is the implementation of it. So essentially, ForkJoinPool is a special implementational case of the Executor service where the focus is around the parallelism, and it does so by utilizing two concepts. First is fork, other is join. So fork is basically creating the subtasks, creating the subchildren of a particular task, and join is like collecting the results from the forked subtasks. So essentially what we are doing using the ForkJoin framework is dividing the tasks into subtasks and then asking the different threads to work on these subtasks in parallel, and finally the result is collected and the final outcome is given back to the caller. So in a way, it's a parallel implementation, it's a parallelized implementation of the divide and conquer strategy. So now let's move forward, and now that we have learned most of the basic concepts related to the ForkJoin framework, we shall start with some code implementation for these concepts. So I will start by creating this package. Let's call this package as ForkJoin. And as I mentioned earlier that we have two classes. One is the recursive task, other is the recursive action. So this particular demonstration would be for the recursive task. In the next one, we will see how we can make use of the recursive action. So what I'm planning to implement is a code wherein I would like to search for occurrence of a given number into an integer array. So let's start with the implementation. So let's create this class and let's call this as search occurrence task. This is going to extend the recursive task and this is going to return integer. So basically integer is the type which it accepts. So if you see the implementation, it's going to extend the ForkJoin task and the ForkJoin task is going to implement future. So now going back to the code, it's giving certain error. So the idea is that it's enforcing to implement certain unimplemented methods. So let's do that. And the method that we need to implement is called as compute. And by the virtue of the type that we provide, which is the integer, it's going to return integer from this compute method. Alright. So this particular class will have a few things. For example, first is it will have an integer array called as ARR. Then it will have a start index. Then it will have an end index. And it will have a value which is called as search element. So let's create the constructor for this class and we are going to initialize all these values. So to begin with, we just have this compute method. So let's say I am going to provide a private method which is going to search for the occurrence in this particular array for a given element. So let's call that method as search and let's implement it and probably we will return the value. So private integer search and let's have the value as 0 to begin with. And what we will do is we will start from the start index, then it will go till the end index and we increment the index value. If the value at index I happens to be the search element, then we increment the count. And finally, when we are done iterating over the array, we are going to return the count value. So this is the search method. So please note that as of now we are not making use of any ForkJoin concepts. So we will introduce the ForkJoin concepts in a while, but for now let's complete the implementation. So this is about this class and let's have the runner class wherein we will be invoking this particular compute method somehow that we will see in a moment using a main method. So let's create a class and let's call this as ForkJoinPool demo. And we have a main method. So we will have an array. Let's say the value is up to 100 and we will have a random variable. Why we are going to need it? We will come to see it in a moment. And we populate this array with certain random values. So for each and every array index, we are going to provide certain value and that would be random dot next int. So that is 10 plus 1. So essentially I am going to populate each index in the array with a value ranging from 1 to 10. And we have a search element which is again a random value. So random dot next int. Then we have 10 plus 1. And what we are going to do is we are going to create a ForkJoinPool. So new ForkJoinPool. And remember that I told in the theory section that if you don't provide the number of processors, it will by default figure out how much parallelism is required. But in this case, let's provide the number of processors as well. So runtime dot get runtime dot available processors. And it's complaining that we should close this resource. So probably we can go ahead with try with resources. Alright, now what we need to do is we need to make use of the ForkJoinPool, and the way to do this is we need to create an instance of this task which has extended this recursive task. So let's do that. Let's create an instance of this task which is search occurrence task, and let's call this as task new search occurrence task. Let's pass the values, which is the array. Start would be 0, end would be array.length -1. These are the indices of the array, then the search element, and we are going to call pull.invoke, and here we will pass the ForkJoin task, and let's capture this as the value of occurrence. Alright, so let's print the value that the array is arrays dot toString arr, and finally system out println %d found %d times, then search element and occurrence, and it should be printf, not println. So let's correct this, and now let's run this code and see its output. So please note that we have not made use of any ForkJoinPool concept as of now. We will do so in a moment. So let's run this, and we can see that the value 9 has been found 6 times. So you could go ahead, implement this code, or probably copy the code from the GitHub link that will be shared in this video, and you could try to execute this, and from this particular value you could validate it. So it's working fine. I have validated it. Now what we will do is we will try to introduce the fork and join concepts. So in order to do so, what we do is we go to the compute method, and we first of all compute the size of the array, which is int -start plus 1, and if the size happens to be greater than 50, then we are going to do some operations. Otherwise I am just going to call the vanilla search method, which is return this search method that we were using anyway. So when the size happens to be greater than 50, we will divide this task in 2 halves, and the way to do this is find the middle index, which is start plus end divided by 2, and in order to create the fork of the task, we will have to first create the task objects. So what we do is we can create the task object, which is search occurrence task. Let's call this as task 1, then new search occurrence task, pass the value. The start value is the start index, the end value becomes the mid, and then we have the search element. Next we create the other task, which is task 2, and then we call search occurrence task. Then we have array, and the start value becomes the mid plus 1, and then the end value becomes the end, and then we have the search element. So if you are familiar with the concept of binary search or any divide and conquer algorithm implementation, you would find it very similar. So essentially what we are doing is, let's say there is an array with some values, right, something like this. So what we are doing is we have to do some processing, some operation on this array. So essentially what we are saying is that, alright, let's say if I have these many values, which is let's say 6 values, so I don't want to do operations on the entire array. Rather what I want to do is I want to split it. So if I were to search this array for all the 6 elements, it will take some time. What if I wanted to search for some value on this particular array itself? It will take less time, right? Because we are doing the search operation on a smaller sized array. So that is the whole concept, where we are finding the mid value, which is let's say somewhere here, and from here to here, this is my first section of the array in which I need to do the search, and this is the second section of the array in which I need to do the search, and this needs to be done till the time this threshold is not met. So for example, let's say this array is somewhat of let's say bigger size, maybe 100 or 200, then in that case first split would be 100-100, second split would be 50-50, and when the size is less than 50, then in that case it will come to this section and it will say, alright, the size is less than 50, the size is less than the threshold, then in that case we can go ahead and do the normal search. But till the time size is greater than the threshold, that is 50 in this case, it will go and break the task into smaller tasks, and that is where we have made use of this task. So the next process in this implementation would be to call fork method on these tasks. So task1.fork, then task2.fork. So what happens is that this task.fork is going to create another subtask. So if you click on fork, you can see that it is going to return the fork join task itself, which is basically this recursive task or whatever implementation you have here. Since this class is implementing recursive task, then this particular fork will also return this recursive task, which is the search occurrence task, but for a lesser search space, right? So if that is clear, let's move ahead and understand how we can fetch the value from these subtasks that we have created. And the way to do that is by calling the join operation. So in a way, you could try to correlate this with the way in which the recursion works, right? And it is pretty much evident by the name as well. So basically it's nothing but a kind of recursive call in a multi-threaded context, wherein you have created different subtasks, and all those smaller subtasks could be picked up by different threads and could be executed in parallel. So it's nothing but some sort of recursion on steroids due to reason that we are making use of parallelism and multi-threading and all those concepts, which are going to give us some boost with respect to the performance. So now let's move and see how we can collect the value. So the way to collect the value out of a task is by calling .join method. So let's say task1.join. If you try to capture it, it will be some integer. Why integer? Because that is the parameter that we have provided here. So you could do this way, or probably we could just simplify it by returning task1.join plus task2.join, and that's the whole implementation. So now let's run this code and see the output. After executing this code, I will give you another walkthrough so things will be much more clearer. So see, this value has been found this many times. So basically 10 has been found this many times. So basically what we have done here is that we have implemented one of the implementations of the task, which is this recursive task, and one of the implementations of the fork join task, and we have certain data structure on which this task is going to be performed, and the data structure of the choice here is an integer array, and our use case is to find how many times a given value is going to be repeated or is going to occur in the given array, and that is the search part of it, and that is what we had in the beginning. Then what we did is we started with the implementation for the compute, and in the compute we first found out what is the current size of the array on which we are performing this operation, and we had a check that if the size happens to be less than 50, then we are simply going to make use of this search method, and if that is not the case, then we are going to break this larger task into smaller tasks, smaller subtasks. And the way to break this is find the middle point in the array, the middle index in the array, and then create two tasks out of it, wherein we have the array itself, then we have a start, then we have a mid value and the element that we need to find. And in the second task, we are going to have the same array, and the search space is provided from the mid plus 1 as the start value and end as the end value. And search element is anyway the element that we need to find. And after we have created this template for these two tasks, we are going to call fork on these two tasks. And when a fork is called, what essentially happens behind the scene is this thing is called recursively with this particular search space, this particular search space. So the search space is going to reduce, it's going to get smaller and smaller, and likewise when this fork is called, similar thing is going to happen. And finally this will keep on happening till the time we have the size, the search space, greater than 50. And after some time the recursion will reach its base case, and then we will like to retrieve the value from that recursive task that we have executed. And the way to do so is by calling .join. There are some other methods as well, but in this example we are going to stick with .join. So let's say task 1 has accumulated certain value and task 2 has accumulated certain value. So both the values will be added, because consider this as a binary tree where we are making calls in two directions, in the left side and in the right side. And once you are done with the traversal at every point of time from every node, you are going to get some value. So that is what the intent is, and that is the way to visualize this code. So that is how we are going to make use of the recursive task to implement fork join framework and do this operation. So before we move to the next implementation, which is for the recursive action, I would like to give you a small homework, and what you could try is you could try to implement this for the use case where we wish to find out the summation of all the elements in a given array. So it would be something similar to this, but I think you should try it out on your own, and it would really help you in cementing the concepts related to the recursive tasks. So now let's move to the implementation of the other thing, which is the recursive action. So let's create another class, and let's call this as workload splitter. And what I'm trying to build here is that there is a class and it has some workload, and based on certain workload it's going to either do its operation on its own, or else it's going to split the workload, or the task rather, into two halves. So this is what we are going to implement. So let's start with the implementation, and this workload splitter class is going to extend recursive action. And as I told earlier in the theory section, that this recursive action is not going to accept or expect any sort of parameter, and neither does it return anything. So let's implement the unimplemented methods, and again the unimplemented method is compute. The only difference is that since it does not return anything, we have a void over here. There is nothing to return, right? So let's have a value and maybe call this as a workload. Let's have a constructor initialize this value, and in the workload what we are going to do is we are going to inspect the value of workload. If the value happens to be greater than 16, then we are going to do certain things. Otherwise this particular task is going to be implemented without any splitting. So let's print some message. We are not going to have any fancy implementation as such. Rather, we are just going to print certain messages to explain the concept. So workload within limits, task being executed for workload, and then the workload value. And what happens when the workload is greater than 16? Well, first start by printing some message. Workload too big, thus splitting, and then the workload is given in the message. So first of all we find the first workload, and this is going to be workload divided by 2. Then we find the second workload, and this is going to be workload minus first workload, right? So again, very similar to the recursive task that we had in the previous section, in the previous example rather, we will create two tasks here for the workload splitter. So maybe call this as first split, then workload splitter, pass the first workload value, and then workload splitter, second split, then call workload splitter, provide the second workload, and we can call first split dot fork, then second split dot fork. Alright, and that's it. Since we are not intending to extract some value, and that is the reason we have made use of the recursive action, so we are not going to call any sort of join or any value that we need to fetch out of this. So that is all with respect to the implementation. Here we are just mimicking certain load balancing kind of mechanism, wherein if needed, if the workload is too high, then in that case we are going to fork two new tasks, and those tasks will be working on that workload. So let's say to begin with, if the value is 64, then the value is certainly greater than 16, then the workload will be divided as 32. So the first load is 32, second load is 32 again, and again this value is greater than 16. So again the load will be divided into 2. So the first load becomes 16, second load becomes 16, and since that is the value, we don't need to go inside this thing, rather we will come to this thing and we will do the execution on its own. So as I told earlier, that there is no any execution as such, rather it is just going to mimic certain behavior around the workload by making use of this recursive action. So now let's demonstrate this implementation and write the code for the same. So let's create a class. Let's call this as workload split demo. Let's have the main method, and we will create the ForkJoinPool. So let's call this as pool and new ForkJoinPool. Again, let's pass the available course, and again this will complain regarding an open resource, so we can resolve this by putting inside the try with resources block. And the way to use this is create an object for the recursive action class that we have created, which is the workload splitter. So let's call it as a splitter, then workload splitter, pass the value as 128, then call pool dot invoke, and let's pass the splitter object, and that's it. So this is what we have implemented. Let's execute this task, let's execute this code and see the output. So here is what we have. To begin with, workload too big, this is splitting, workload too big, this is splitting, and so on and so forth. So 128 got split into two halves, 64 and 64. 32 got split into two halves, 64 rather got split into two halves, 32 and 32, and so basically 32 and 32, and this one is 32 and 32. So as I told earlier, that these things are executed, all these tasks are executed by threads in parallel. So based on the thread scheduling, you are seeing that we are having some sort of not in sync kind of response, but the idea is that the number is getting split into two halves. So 64, each 64 is getting split into two halves, right? One half here, other half here, and further the 32 is getting split into 16, and since 16 happens to be well within the reasonable limits for the workload, we have this message that workload within the limits, task being executed for the given workload. So these are the messages that we are seeing. So that's it about the implementation of the recursive action, and that is the way in which you could implement it. So that should be it for this particular topic of fork join in Java. Thanks for staying with me till the end of this video. As per one statistics, Less than 10% people finish watching a tutorial video once they start watching. Well, guess what? You are the top 10% of the lot. You are awesome. So where do we go from here? I am hopeful that you learned a few important concepts which lay the foundation stone in learning the super awesome yet complex topics of multithreading and concurrency. I sincerely request you to start implementing these newfound concepts in your day-to-day software engineering activities. If not, at least try reading some code which makes use of the multithreading concepts. Doing these things will cement all the new skills that you have learned and acquired with me in the last couple of hours. Needless to say, the concepts in this video are introductory and foundational in nature, yet they are very important. So what this means is there are even more exquisite and complex topics which I did not cover in this video. But whatever you learned should be good enough to get you started. Good news is that I am already working on another video which will cover more advanced topics in more details. I hope you are excited. So to summarize, first thing is start implementing the concepts learnt in this video. Then read code which makes use of the multithreading and concurrency. Third step is watch out for the next video on the more advanced topics in multithreading. And most importantly, did I tell you that I also have an YouTube channel? Here is the link. Please do subscribe. It would mean a world to me. With this, I sincerely thank you once again for your time and attention, and I hope that you found this video useful. Hope to connect with you again in my next video tutorial. Thanks for watching.